by the platform that view is that which is from many companies that work with. So I think which don't talk, but the first start.
Start. Okay, so and say first, and just in case, leave. Tells would be that the to reach the reference what so it will in 2015 look like the same architecture and front end still very small language small language. And was really one of this. It was called separate the code. We have languages, but types of reduction. Fast picture the best. So, and also started external from one in Echo and one Microsoft for Sharp for open source. And so I had to produce but still is not and so because they wanted to make this intermediate step, which is still come back to that later. Will so now this interpretation and of them here, but there was in that version of the AI framework. By abduction, would break the full power this memory for the device, and so it looks like manipulation. On top to last like this. So on the front hand side, we have the languages, Erlang and Hack, and based on a new intermediate textual, which I and we still have so we have this Python prototype, really functional development. Checker. We had 9, and with 3 of them got absorbed into rewrite side. And by default, we have 50 types variables. So about ways in which that still for is makes a new language and analysis. So but the ones who are provided rights and checkers. Apply archive, but it's shared for. That day, so still very simple instruction. System state basically go to between those. Because it was you have a lot of work. Basically a compiler. And much of you still have a compiler, but some there's a lot of there's some things that there are no that have so become organically attackers to say form the it is hard to work backwards from this. I did for front end silver is not so is that. And when we create we call textual, it's very in it will show you to so you from there's even but also directly, for instance, for the Python, there's a from her and to work with. From shared in two ways from intermediate directly for the front.
Int when you but the
one we're bring one into fact. You have to tell the types everywhere. And so where it would be types in any pieces, we'll infer them for. But okay. And everything now framework. It's a great platform. A component with here, which and the piece that lets you and you find infer to work. But it's analysis, you run analysis on bar. It, by internet, then it compute or it somewhere and return it to an based in exchange. You get mechanism. It's really what
is analyzed at most once. This means the summary has to cover all possible, or are they partial?
Be possible and good enough to cover sites. More true is how they we don't want to produce.
Yeah. If you general summary that might arrive more expensive.
Yeah, that's true as well.
Okay,
you have to be very general and express everything in terms of your inputs, and that might be overkill in some cases, but that's hard to know.
Hi, sorry, I got another question. So, what happens if there is like a first-class function calls like this function pointer? I don't know which function it is. So, what do we do here?
If there's a function pointer?
Yeah, then I don't know which function it is really.
Yeah, so like I was saying, so if you take a function pointer as argument, then when you call that function, Infer doesn't know what it is, so it doesn't know, it can't get the summary. For that function. So in that case, what we'll do, we'll still compute a summary, just treating the function pointer as an unknown function, and sometimes that's good enough. But we also, if at some other point you have a caller of that function that passes in a specific function pointer, we know the function, we can go and reanalyze the original function by saying, hey, by the way, this guy is this function, and so then when we reanalyze the function, at the point where the function pointer is called, we know who we're calling, so we can pretend that's what gets called.
Okay, I see. Thank you.
And we compute a new summary we call specialized, and so it's specialized to that particular value for the function pointer.
How about recursive functions?
How about recursive functions? So right now, it's very simple-minded. When we hit a recursive call, the analysis, this engine will return an empty summary and say, oh, I don't know this function, to prevent loops. But it's not a fundamental limitation, it's just there aren't that many recursive functions in the code bases we analyze. But you could imagine at least unrolling this a few times and even computing an invariant, repeating until you reach a fixed point.
So when you call it an on-demand analysis, does this mean that it's only computing information on demand, or is this still a whole program analysis? So from this picture, it looks like you start from like the main functions and then analyze everything reachable from there.
No, that is not what we do. Yeah, so I was going a bit fast. But so usually we proceed more bottom up. It's on demand in the sense that if you're only interested in something reachable from main or something, you can start at main and it will explore the call graph for you. And we use that property to do at Meta. One of the main uses of Infer is analyzing code changes. And so we use that very heavily to analyze code changes because we start from only the code that has changed. That allows us to analyze just a fraction of the code. But you can, it's on demand in the sense you only analyze what you need. But also you can start anywhere in your program and the on-demand analysis will compute what's needed for that. And we use that both to analyze only a fraction of the code or even when you analyze the whole code base. We can't know in advance what gets called because that information is not entirely in the static call graph. For instance, when you have function pointers or dynamic dispatch or other things. And so on-demand allows us to be flexible here and still go and compute summaries when they're needed.
And then one more question. So it sounds like you are assuming that a call graph is given in advance, or are you computing that on the fly?
No. That's why I was trying to say we don't have to assume that because the analysis this has the ability to go fetch function summaries at any point. So even if you don't know the call graph.
But how do you know which functions are being called then? If you have again
well, your analysis will be looking at the code, right? And when it sees a function call, it says, "Oh, I need the summary for that function call."
Okay, so if you start in a function foo that calls some function that you don't know until you know how foo is being called. So does it then like go backwards and see where foo is being used, or?
No, we don't go backwards. So I think that you're asking the function pointer question again.
For example, yeah. So if especially now that you have, I see more dynamic languages like Python on the list, where you have a lot of very dynamic behaviors. Dynamic
so in Hack we do that a lot. We like so you have to when we analyze a function, we do the best we can with the information we have. But if at a later point we know, actually I know the type of this object is as a concrete type now, and it's this, you can go and reanalyze callees in those cases if you need to.
Thanks.
Okay, so next I want to talk about the AI framework. Oh, that's a bit dim, sorry. Maybe so just like the on-demand analysis gives you an interprocedural scheduler for free, the AI framework does the same thing for intra-procedural. So when we have source code, we translate it to CIL, which becomes this big CFG. And here I cheated, I didn't write actual CIL in the nodes. It's still the C code more or less, because it gets a bit too gory. But so now if you were to start from this, you'd have to do a whole bunch of logic to analyze CFGs, but the AI framework does that for you. So what you need to provide for this is just a few ingredients. So first of all, you have to describe what your abstract domain is. So we know what we're computing. And so in particular, you give it the empty element of your domain, and then AI framework will start the analysis at the start node with the empty state. And then the main piece after that are transfer functions. So how each instruction in CIL affects the abstract state. Basically symbolically executing an instruction on an abstract state gives you another abstract state. And AI framework will use this transfer function to propagate the state from node to node. So we'll explore the graph this way. And then join points, we need to do something else because now we have an abstract state coming from each edge. And so that's where we call a join function you provided for your domain, borrowing from abstract interpretation lingo. And finally, at loop heads, we'll call your widening function with the number of loop iterations done so far. So if you give all that, then in exchange you get an interprocedural analysis. And here I made it go forwards more or less, but you can customize this. Can be forwards or backwards. You can analyze nodes in some given in some more specific orders, especially around loops. And I say interprocedural because here we're also using the on-demand aspect. So when we're analyzing that first node here, we have to make an on-demand call to get the summary for this new node function. And on-demand will give you back a summary. A summary is something you define yourself as well. And in fact, you have to create those summaries when you analyze functions. And a summary can just be the state of your analysis at the exit node, or it can be anything you want from the result of the whole analysis. So if we shake all of that together, we get an interprocedural analysis with just these few ingredients. And you didn't have to worry about how to explore the CFG or how to explore the call graph. Yes. Mike, please.
Hi. So what is T in the summarize function?
T is the is your domain, is your abstract domain. In fact, I
is
lied
it domain
here
or a fact from the domain?
It's the domain. It's the oops. So so it's the type of your abstract states.
So it's like an abstract state.
Indeed. Yes.
Okay. Yeah, I think this relates to my previous question because here on the next slide, this seems to me like the summary database is indexed by the input fact that you reached the function with, right? Like otherwise, why would you have to pass a T to the summarize function?
Is the function you're analyzing, right? And you start from empty when you start analyzing your function, so you don't know anything about your inputs.
Okay, then what is the T that you're passing to the summarize function?
And actually, I lied. It's not quite the T. It's this whole invariant map of the abstract state at all the program points in your CFG that you pass. But usually, you take the one at the post. So this.
I see.
A lot of analysis, for instance, in Pulse, which computes pre and post for your function in a forward manner. The state you get at the exit node is pretty much the summary. It's the inferred precondition for the whole function all the way to the post.
Okay, so the T is okay, I think I get it now.
Yeah.
Okay.
It's just, yeah, technically, a lot of the time T is just the summary type is just the domain type, but that's not true of all analysis. So.
Okay, thank you.
Yeah.
Yeah. So when you run into a loop, will you always iterate to get to some fixed point, or you will do some balance between the precision or the time cost here?
So the AI framework will iterate until it reaches a fixed point. I think it stops at 10,000 iterations or something after we had a few infinite loops accidentally. But you can use that to do whatever you want. Nothing in this framework checks you're actually building an over-approximating abstract interpreter. So, so all these functions you have to give can do arbitrary things. But yeah, so it reaches a fixed point in Pulse, which is under-approximate. We use that we can emulate fixed unrollings with this by just pretending we've converged after a few iterations by returning the same abstract state again.
Okay, I see.
Thanks. You said that you always start in the empty state for your domain. Is there anything that you do for the function arguments, or do they just become top, more or less?
Well, your empty state can look at the function arguments.
Okay, so it's an empty state per function, basically.
Yeah, you get to create the empty states from the function you're analyzing. Yeah.
All right.
It was a simplification, you're right. All right. So the final piece I wanted to talk about is Pulse. And Pulse is sort of a platform itself as well. This is where we write a lot of our new analysis, a lot of our new bug types are on top of Pulse. And you want to use Pulse when path sensitivity matters, and you want to care about infeasible paths and things like this, and you don't want to report on them. It has a built-in memory and value analysis engine that's very precise. It was co-developed with incorrectness separation logic, so you can read all about it in a few papers. And from the get-go, it was built as a bug finder, not as a prover that your program has no bug, because that's how we use Infer. We use it as a bug finder. But it was also built as a sort of extensible engine so that it would be easy to work with for our team and others. So I just want to give a brief overview of what's in Pulse, how it works. Well, maybe not how it works, but let's see. So I just want to describe basically the abstract state of Pulse, and then maybe we can all infer how it could maybe work. So the Pulse abstract states represent the state of the machine. So it has a store which assign abstract values to program variables and the intermediate variables that SIL produces, which shouldn't be called logical variables now I think about it. And memory, so this is the only part that mentions program variables, which are mutable. But then everything is in terms of these abstract values, which have an immutable semantics as the program executes. So when you assign to a program variable, you will make up a new, fresh, abstract value to represent that. But the old value it had will keep its value. And so the memory tells you what values point to other values, either via field accesses or dereference. And then there's this sort of mysterious extra map of attributes, which is a bit of metadata telling you facts about your values, such as, oh, this value is invalid because we called free on it, or this value must be valid because we dereferenced it, or it's been allocated, so it should be freed at some point, etc. So for instance, assigning null to something in memory, our state would look maybe like this just before. We know that L is some abstract value VL. And in memory, we know that VL has a next field that points to some value V. When we assign to it, in the post state, it points to some new value, V0. We know V0 equals 0, and we know that it's invalid because it's the null pointer. Okay? So what Pulse works with is not one of these states, but at any time a pair of these states, one that represents the inferred precondition for the function so far, and one that represents the current state. And there's a formula as well, like V0 equals 0 on the previous slide was actually not part of this base domain. There is something that's shared between the pre and the post, thanks to the fact that values are immutable. And that's sort of all the pure facts about values, like equalities and inequalities. So coming back to this, we would start in an empty state, which is pretty close to empty, amp. And then when we analyze LR next gets null, we'll make a few inferences about the precondition and the postcondition. So we'll say, so L had to be allocated from the beginning. And now I changed the precondition to this. And also because I dereferenced VL, I know it must have been valid, a valid pointer. And I make a note of that in the precondition. And in the postcondition, it points to a new value that happens to be equal to 0 and is invalid. And this interplay between valid, must be valid and invalid is very important in Pulse. That's how it tracks null pointer dereference and the like. It's when these two meet. So in order for Pulse to report something here, it has to have strong evidence that something wrong happened. So it must know that something became invalid. It saw the assignment to something wrong, something invalid, like the null pointer, and then that you're trying to dereference it as well. Yes?
If you're going to get to this later, by the way, that's totally fine. I was wondering if you have multiple parameters of pointer type, what kind of assumptions you make about aliasing, or whether you actually figure those out based on your analysis of the body, like the same kind of thing, where if you see equality checks, you might
so
put that in the precondition.
Yeah, equalities are part of our language of formulas here. So when things are aliased within the function, no problem, we will be in the abstract state. But if we don't know anything else, by default we make the assumption that things are separate. So this is still separation logic at the heart, and unless we know otherwise, things are all separate in memory. And if we discover that this is not the case, for instance, at a call site, there's some aliasing that wasn't computed in the summary, we use our cheat code again and go and reanalyze the callee with the fact that and start with these aliases.
Can you go back one slide?
I think so.
Maybe one more. You had a slide where the code was, and then you had two empties in it.
Oh yeah.
Yeah. So does that mean you start from the middle and then you like go back and forwards?
No, that's the start of the function.
Oh yeah, but like, why do you have two empties?
Aha. Yeah. Sorry. One is the precondition and one is the current post condition.
Okay, I get it. Okay, thanks.
Yeah. Will you tell us what is a join in this domain?
Kind of. Okay. Yes, this is coming. So we're not done building the Pulse abstract domain yet. But first I wanted to just say a few words about the formula, although I don't really have time. But basically, there's a little SMT solver inside of Pulse that can do reasoning on linear arithmetic, equalities and inequalities. It pretends everything is rational, so it's not very good at integer or bit vector reasoning or disjunctions as well, because it doesn't really do a lot of SAT solving. But for programs, that's often enough. And so, in the interest of time, I go fast here, but why is it important to have an SMT solver inside of Pulse? Well, when you have a realistic program, you have lots of patterns like this. This can be right in the code, or this can be because of interprocedural analysis, and these live far away from each other. So in this case, if x is greater than y, we assign p to null. And so when we come back from the if, we get two states, and this is where the join of Pulse comes into play. So here we've applied a join, and the join is just accumulating states. And I'll say more in just a second. And so it's important to know which case corresponds to which conditions, because when you see code like this afterwards, the SMT solver has to tell you that you cannot be into the branch where P is null, because that would be a contradiction. And so you know it's safe to dereference P here, I think. Okay. So now we're ready for the Pulse domain. It's a path splitting domain, so it's actually a list of those states. And there's a hard limit on the number of disjuncts we accumulate. And together with finite loop and rolling, this gives us an under-approximating analysis. So it only covers some behaviors of the program, but the ones it covers, we are sure are true behaviors. And so summing up, the domain is a list of pre's and posts and a formula, and each pre and post has some model of the memory. And this is actually also a simplification, but by and large, this looks like this. All right. last thing I wanted to mention is how to manipulate pulse states. So this is a model of a C++ swap function which swaps two pointers. And this is the old way we would write this. So it already had some facilities to let you write this somewhat easily. So you can see it's reading two fields and then writing two fields. But you have to write some boilerplate. There's some very mysterious symbols along the way. And you carry this abstract state around, which is the abductive domain. But still, Pulse does a lot of work for you, because you're just saying, I'm reading and writing in the memory, and behind the scene, Pulse will abduce what it needs to the precondition and check that pointers are valid and do all sorts of things. But now we have a nice DSL, we call it. It was just a monad for manipulating pulse states. So now the state has kind of disappeared into the monad, and the code is nicer to read, hopefully, and nicer to write. Okay, so that's all I had. Infer is a platform in more ways than one. And yeah, it's all platforms. So we have platforms for adding languages, the on-demand analysis. You can build directly onto on-demand if you don't want to use the AI framework. Otherwise, you can cast your analysis into AI somewhat, even use that. If you want a precise model of the memory and values and all that good stuff, you can build directly inside of Pulse, and we try to make that easy as well. And just some things that are top of mind for us at the moment, which may or may not materialize. This is not contractually binding. So we're thinking about adding new languages. Now we have this nifty textual interface that makes it a bit easier. So Python is an important language at Meta, as is Swift, which has kind of replaced Objective-C in a lot of use cases. We are thinking about going beyond under approximation to get better coverage of programs in Pulse. It would be really cool if Infer could suggest fixes for the bug it reports, so that developers had a little help there. And finally, OCaml 5 is a thing now. It's multi-core. Infer, I didn't talk about this, but it's very, very parallel. The analysis scheduler actually schedules the analysis in parallel over multiple processes, but they have to share their results via an external database, and it would be really nice if they could just use the shared memory instead and threads. So we think there would be a lot of value in moving to multi-core here. So yeah, I stop here. Thanks. Any more questions?
So you mentioned adding over approximation. Is the goal there to, after you've sort of found a bunch of bugs and fixed them, to then prove that you don't have any bugs anymore? Is that like a verification goal, or what are you doing with the over approximation?
It is not a verification goal because I don't think we can achieve verification with for two reasons. One is Infer is a fully automatic tool, so it will have to be somewhat inferable by Infer that your program is correct, which even for correct programs would be very hard. Second of all, I don't think there are any correct programs in the stuff we analyze, so I don't think it's something we can achieve.
So what is the goal of?
All right. So the goal, the goal would be to. So when we analyze a program, we throw a lot of states away, and we don't know what was in those states. So it would be knowing what was in those states. Even a coarse approximation of it would give us some idea of if we missed something important or not. And in my dreams, I have this idea that you could start with an over-approximating analysis, and then when it finds a problem, but it's not sure because it's over-approximating, it can go and replay with an under-approximating analysis to see if there is an actual problem. Or we can do something a bit in between, like by abduction was doing before, which is trying to join states as much as possible when it doesn't lose too much precision, and then yeah, work with that.
Thanks.
So these are a few possibilities.
Yeah, seems very cool. Does Pulse or Infer in general work when you don't have all the code for a program? I'm thinking, well, I'm not sure how the Java front end works, but like in open source, you'll have some source code and then you'll have tons of third-party libraries as jars. And I don't know if you have a bytecode front end or how that would work.
Yeah, we do have a bytecode front end.
Oh, okay.
But
So in principle, like, would you recommend translating everything to SIL and doing analysis over that whole program, or?
No, I wouldn't. I mean, I would normally no, because it's expensive, and so you will always have unknown code, even if you analyze all the bytecode. And you will have native functions, you will have some built-ins, so it's unavoidable. And so the Infer analysis, the way they're built, they're pretty they degrade gracefully in the face of unknown code, so it's not too much of a big deal usually. So yeah, each analysis will have its own heuristics in the face of unknown code. Of let's scramble the memory here because it looks like this could modify this object, or yeah, I don't know. It's not perfect, but it allows us to get past it.
Yeah, so can we consider the seal layer is kind of stable now, because you want to support a lot different language, front-end languages, but they are quite different. So will it like need necessary to be changed a little or be extended a little bit when you're trying to support new language that has like its own different high-level semantics information that you want to catch?
Well, there are several ways to interpret stable, but I mean, at the binary level, it's not super stable because every so often we change some data structures. But at the high level, it's been stable for many, many years now. It's still the same 4 or 5 instructions. Sorry. And when we add new languages and we need something SIL can't provide, usually we just encode that as some function call to a built-in, and then analysis backends that actually care about precise semantics of things have to know how to interpret that built-in.
Okay, thank you.
So that's a convenient escape hatch we use often.
So I'm a little uncertain about the structure of these different components. So is Pulse still building on top of the abstract interpretation framework?
Yes.
Like
as this diagram makes clear.
Yeah, but it doesn't seem like abstract interpretation style. It doesn't seem to fit into that abstract interpretation
yes,
structure you described.
well, yes, so the AI framework is called abstract interpretation framework, but really it's just a functor. You give it a domain with some functions for join and widen and a transfer function, and then it builds an intra-procedural scheduler. So it's really an intra-procedural analysis framework. And it uses, because it uses vocabulary from abstract interpretation, it's useful to think of it in those terms often, but you're right for Pulse. It's really stretching it. But I mean, but still, when you come back from an if, you have an operation you have to do. We call it join, and yeah.
Okay, and then for example, this finite loop unrolling you mentioned, that's also encoded in.
Yeah, it's encoded as something that converges in a abstract interpretation kind of way. But really, what it does is using the number of loop iterations. When it's bigger than the threshold, it will return the previous state and pretend. And then the AI framework will say, well, that implies the previous state I had, so you've converged, so congrats.
Okay, so it's in a sense an unsound widening function.
Yeah, well, you can give it an unsound widening function. It won't, there's no...
Okay, and then all this still builds on top of this on-demand analysis for interprocedural.
Yes,
okay.
Correct.
That's it, thanks.
Yep, one more.
unless someone else has a question. Yeah, I was curious how Pulse handles virtual calls or higher order functions. Is that some logic built into Pulse, or is that something language specific that happens somewhere else?
So there are some language specific bits. So Infer, there's still one part of SIL that I didn't show. So SIL is these CFGs of instructions, but there's also this type environment we have on the side, where you have your class hierarchy, typically. And Pulse can query that to resolve method calls. So that's one part. And the other part is this specialization technique I mentioned, where when Pulse goes to a method call and it realizes it doesn't really have enough information to fully resolve it, and it's still abstract, it will make a note of it, and then if a caller ever calls this function and has a concrete type for that object, it will reanalyze that callee with that extra information. And now, when we reanalyze this, we can fully resolve the call and produce a more accurate summary for that case.
Yeah, the reason I asked is because if you naively consult the class hierarchy, that might go against your goal of having no false positives, right?
Yeah.
So that's why I was asking specifically about Pulse, if it only analyzes virtual call targets that it can actually prove are feasible.
No, yeah, we don't have a mode like this. I mean, it would be easy to add, but not very valuable because it would stop a lot. And it would stop at unknown calls as well, right? The only sound thing to do when you have an unknown call is return bottom. And same with a virtual call you couldn't resolve. And so that would cut down the analysis in a lot of useful cases.
So then you might get false positives in the presence of virtual calls.
Yeah, absolutely.
Okay.
And unknown functions and weaknesses in the SMT solver and
okay. So no false
imprecisions in the
positives is
front
like
end.
a sort of top level aspiration, but there are various corner cases where you still get false positives from false.
I mean, like all soundness theorems, it has a precondition that says, assuming the semantics is like this, then no false positives. Yes.
Okay.
I know that Infer is in sound. Can you have tunable soundness, or do you have tunable soundness?
In what way?
Like you push a button and can you have sound analysis?
Well, yeah, that's kind of related to that, right? Well, if you don't have any unknown calls, then Pulse is sound for bug catching, and if you don't filter anything, by abduction is sound for verification. So, but we don't really have switches to stop in case there's something we go beyond those hypotheses.
Okay, I think we'll stop here. Thank you very much, Jules.
Okay, thanks for all the questions.
And the next talk is in 30 minutes after the break.
Okay, hi, I'm Dulma. I'm from the Infer team at Meta as well. And I'm going to speak about a checker that we built on top of polls for finding retain cycles in Objective-C. So this is an example of how to build something on polls, and also how we go about building such a checker, making it production ready. So what is a retain cycle? Something happens in Objective-C, but also Swift, that two or more objects have strong references to each other, and that prevents them from being released from memory, and that can cause memory leaks. So something that causes many memory leaks in the apps, and it's easy enough for developers to do. So we are focusing only on Objective-C, because that's the front end we have. So we have a Clang front end that covers C, Objective-C, and C++, and we need to build a Swift front end to be able to handle Swift, which hopefully we can do soon. So let's start with some examples of what does it look like. So this is a class view and a class delegate. The class view has a property of class delegate, and the class delegate has a property of type view. And then in the implementation of delegate, we have an initializer, and there we build a new view and then assign self.view.delegate equals self. So then at this point, that's a retain cycle, because they are both pointing at each other, and the pointers are strong, so they're retaining each other. So the solution to not have a retain cycle in this case is to write one of the properties to be weak, which means you still have the pointer to that object, but you are not retaining it. So it won't be increasing the retain count on the object. And so this is kind of a common pattern. That's kind of what the developers should do in that case to avoid the retain cycles. Another common pattern is to do with Objective-C blocks, which are the closures. So here we have a class user that has a property callback, that's the block, and a property name. Then in the initializer of user, we have that self, we assign callback to self, which is the block, and inside the block, we use self. So using self in a block means capturing it, and that means retaining it. So that also means self is retaining the block, and block is retaining self, so that's also a retain cycle. In this case, the solution that is recommended is to use a weak pointer to self, and then capture that one, and then inside the block, kind of making the weak pointer strong again to make sure it's still there, and then if it's there, use it. So that kind of the pattern that the developers use to avoid these kind of retain cycles. So yeah, we want to build a checker for this in polls. So thankfully we just had Jules talk, so you know more or less how polls works. So we basically use the abstract heap of polls and the abstract interpretation that polls provides, and we try to find cycles in this abstract heap. And so we just need to check that there are cycles and that the references are strong between the objects. And then in that case we report. So we need two parts to report. We need that there is a cycle, and we need that the references are strong. So yeah, then I'm going to go through different aspects of the implementation. So one aspect is where do we check, where do we report? And so for making it more in sync with the definition, we should report at the place where the variables are going out of scope, because then that cycle won't be able to be broken later. But we tried that implementation in the past, and it led to not reporting very much, because So basically, we just learned that Pulse gets rid of some disjoints on the way. So that leads to not complete code coverage. So we have the problem, so we just need to make sure that we report as soon as we find a cycle to maximize the ones that we report. So that's what we're doing. The option 2, and that means we have more reports, but we can have some false positives because it could be that the cycle is created but later broken. And in that case, then we'll report anyway. But in practice, hasn't been a problem. Okay, so let's look at error messages. So this is an example again, the first example about the class view and the class delegate and the objects returning each other. Question?
Sorry, I had a question on the previous slide. Yeah, why do you get more false positives if you report the cycles as soon as they're created? Is that because they might then get, the cycle might get removed later on?
That's right there. So maybe they just create the cycle temporarily and then assign one of the variables to nil afterwards, and then that breaks the cycle.
Okay, thank you.
So we have this example, so let's look at the error message here. So we say retain cycle found on line 22 between the following objects: self arrow view assigned on line 21 and self arrow view the delegate assigned on line 22. And so we use an internal decompiler to give meaningful name to both abstract values. So that's how we get those names. And then in this example about blocks, so we say the same, but we say self arrow callback is one of the objects assigned on line 13, and then in the other one we say self was captured by this block defined here. So we can give this information about where are the objects involved in the cycle. And so one thing that can be improved later is that we say precisely where the variable is captured. At the moment we say it's captured by the block, but it could be more meaningful if we say it's captured here at line 14, because they see, otherwise they need to look through the whole block to see where self is actually used. That's something to improve for later. So let's look at how this, yes.
Could you just remind us what is a block in Objective-C, how it works?
I mean, it is a closure, just like lambdas in C++, etc.
Okay.
So let's look at how this looks inside Pulse. So again, let's look at this example, and we'll look at the implementation of this bit, the execution of that bit, where we want to assign self to the delegate. So first we get the view. So this is SIL code. First we get the view, then we assign the delegate to that view. And so at the end of this execution, a simplified heap of Pulse looks like this. So we have the roots and 2 and 3 and 4 and self. And then we have the memory that looks like this. V1 points to V2, V2 points to V6 via view. Then V6 points to V5, V5 points to V12 via delegate, and V12 points to V2 again. So that's the cycle. And an important thing is that these accesses need to be strong. So we check all that. And also, we have information about which class it is in the attributes. So that's where we store the types. Yes.
You mentioned that these two references have to be strong. What about the cycle is longer than just these two? What happens with the rest?
I guess everything needs to be strong, but generally, yeah, the pointers need to be strong as well. Yeah, we check that too. Right. so the class. So we also want to only report on Objective-C classes, so we check that the values in the cycle are either pointers or Objective-C classes. Yes, please.
Yeah, sorry. When you say pulse state, does that mean that this information is already tracked by pulse by default, or you kind of plug in to pulse with extra information that you want tracked in its memory analysis, like whether pointers are strong or weak or that kind of thing?
So I will get to that later, what we do about the pointers being strong or weak. That was something we had to fix towards the end. But other than that, everything was already in pulse. And I will also mention later an attribute that I added just to avoid duplicates. So yeah, we can add attributes, we can change pulse, whatever we need. Right. So for closures, we did have to do a lot of work in pulse to implement the closures in a way that let us execute them properly and also find retain cycles with them. So we interpret them as objects, and so basically when we have a closure, we say this is an object of type the name, the internal name that we give to the closure, that's the kind of type name. And then the variables become, the captured variables become fields of that object. I'll show an example in a minute. And yeah, that helps with this check because it's then trivial to find cycles between blocks and their captured variables because it's all the same objects and fields. So that was the example we had. So in this line, when we assign the callback to self, this is what happens. So we have set callback, and there we have, this is the SIL again. So this is the closure object, and this is telling us this is the closure we're talking about, and these are the captured variables. So self is captured. And so after we execute this impulse, we again get this heap. So we have that the type is the type of the block. We have the root itself, and then again we see V1 points to V2, V2 points to V6 via the callback, V6 points to V4, V4 points to V5 via this self-captured by value. So that's the field of the closure. And then B5 points to V2 again. So that's basically the block pointing to the captured variable. And that's, again, another cycle that we can find in the same way. And we take into account also the types, so that we have this, one of them is an Objective-C class, and the other one is an Objective-C block. So these are the only ones we want to track. Okay, so let's talk about a few more improvements to the implementation. So one is about duplicates. So one issue with reporting right when the cycle is created is that we want to continue the execution after that, and then you will just keep seeing that cycle later more and more times. So one solution I found for this is to add an attribute. So every abstract value that is involved in a cycle after it's reported gets this attribute in reported retain cycle. And then when we see the attribute, then we don't report again. So it's quite a clean way of avoiding duplicates. And then, yeah, then this is the bit that is less fun but very important. So all the implementation is run and the test pass with our small examples, but that doesn't mean we can ship it. It means we need to then start looking at clear code. So we look at how the checker works in clear code, and if it has false positives. And then we iterate from there. Look at the false positives and try to find what are the problems, what needs to be improved, and fix them. When we see a good, I mean, we won't aim for 0 false positives, but we aim for a good checker that doesn't have too many false positives before we release it to the users. So, and then Finding false negatives is harder because obviously we don't know where they are. So for that, we generally work together with developers that know what are the in this case, retained cycles that happen. And then they give us the examples. We try to run the checker on these examples to see if the checker can find them, and if not, why, and improve from there. So we need to do all this work and iterate on that. And so I won't go into details of the false positives we found, but just to give an example of what kind of issues. So we found front-end bugs, or missing front-end feature, or an incorrect model. We were also reporting issues when polls saw that the objects were nil. That also leads to false positives. So we fixed all that. But I mean, in this example where I looked at all the reports for this particular checker, it was never polls' fault. So we had a question about the false positives of polls in the previous talk. And so it's an example of like polls generally is pretty accurate in its own execution. That it was never like polls was completely wrong in the execution. So for false negatives, so we had this basically implementation problem of where we find is this field access weak was in the type environment. And so the Clang frontend produces a type environment for each file. So there are different type environments. And sometimes the type environment that we have at hand when we're checking the retain cycle was not the correct one. And so we were missing this information about whether this field is weak or strong. In that case, we were assuming that it's not weak, so that we don't report false positives. But we were missing many reports. And then, yeah, the solution we found was to just, because this is just a Boolean, we just store it together with the field name in the SIL instruction, and then that gets passed to the polls heap. So it's kind of in the right place. We don't need to find any type environments. And the number of issues we were finding increased over 100% after this. So it's an example of kind of thinking outside the box. Like you get fixed in one implementation way of doing things, and then try to think differently. Yeah, the other false negatives are just because of polls. So it will get rid of many disjuncts. It will miss many code paths. So there are many issues that we won't find because of that. And there's just improvements we want to do to polls to try to cover more code. So that's basically the future work on this checker will be that. So try to look at ways of finding more issues and then improving the error message with more accurate information about the captured variables. And that's all I have. Thank you. More questions?
I can ask the first. Yeah, about the type environment, you mentioned that with the Clang frontend, we have several type environments. So what is the story behind that? Could we merge all this information into a same type environment? Because I know that other frontends have another point of view.
Yeah, so in the front-end part, that's all done in parallel. So each file gets translated individually, so the type environment gets added like that. And then we could have an extra step in between front-end and back-end where we merge it. We've never done it. We've thought about it. Don't know if Nikos has any ideas.
I think that in Clang the problem is that the same type name can have completely different definitions in different source files, right? You can, depending on what you include, your types will have different definitions. So you can't just merge It is a very local view of the type environment that you have in C++, right, or Objective-C. So I don't see how you could merge. Yeah. And actually, does that make sense?
Yeah.
Yeah. Actually, I wanted to ask a question as well. The examples you showed have cycles of size 2, but in the pulse heap, it's not actually 2, it's longer. Does this mean that you automatically get reports for longer, for cycles of longer visible length than 2?
So the examples I showed have 4 elements, but one of them is the pointer, the other one is the object. So it's a pointer to the object. So it's no point showing 4 things to the user. So basically internally then I just remove the 2 of them that are not the pointer and just leave the 2 that are the pointer, and then those we use the compiler to find a meaningful name for those, and then that's what we show. So yeah.
But would this already work if you had 3 objects in the cycle?
Yeah, it works if you have any size. I mean, in practice, we haven't found that many cycles that are like many objects, just because of that would be just a lot of execution that pods need to get right to get that cycles.
So in case we get a Swift front end one day, is it still a property that makes sense for the Swift language?
Yes.
Do you think in general that the current properties that are checked for Objective-C could be still of interest for Swift? Did you think about
yes.
that?
So in the case of retained cycles, that is the case. They still have them in Swift, and they're interested in getting that checked. And so we will need to see case by case, because obviously the languages are different. So I think nil problems are less of a problem. So yeah, some checkers would be useful, some less useful. We need to see what are the problems they have and build new checkers as well.
Okay, not more. Yes.
Thank you for the talk. I wonder this cycle between variables, could it be used for other properties and like reference counting, loops, like for example detecting circular lists or things like that, where you could try to find cases where you're not intending to have circular data structure but you do, or things like that?
Yeah, absolutely. It's the same.
Have you tried this analysis on like something else than Objective-C, for example C or C++?
I mean, I saw examples of reports that were including C slots as well. I just tried to remove them just to avoid false positives, because what we care about is in Objective-C. But even without trying, there were C objects involved, so that it's just checking cycles in the heap. You can check for any cycles with similar kind of ways.
Yeah, I think in C++ with shared pointers and other ref counted things like this, you could check a similar property and get useful bug reports of unintentional retained cycles there as well. Yeah, so that could be cool.
So.
Yeah, I was curious. So in practice, when the kind of bugs you have found, what was the size of the cycles? How many interprocedural calls did you follow to catch them? Do you have some numbers about that?
I mean, just from what I've seen, so I haven't seen, I think, many that are more than 2 objects. It's a very common pattern, the self and block. And also the delegate being weak, so kind of 2 objects returning each other. But the examples that I know exist have 4 or 5 objects, so we're just not getting there yet. And in terms of interprocedural calls, yeah, there are a few interprocedural calls. Also, a specialization of blocks. We need to be able to see what's happening with the block exactly, calling the block and going back.
And how do developers react when they see this tool working?
I think they like it. So every time they have seen them in diff, so I have mentioned it to them that cycle is there, they want to fix it. We made a post to them. There were a lot of comments about how good is this. So it is a problem that causes them a lot of hours to actually fix or find. So we're not finding all of them, but the ones we find is easy for them to fix because it's a diff time. So it's when they submit the code. So it's better than later they get the task or you're crashing the app with this retain cycle, fix it.
Yes, because for them, what is the symptom of the problem? It's just a memory leak, and they don't know where to start to look at. I mean,
yeah, that could be an issue. But there is also a dynamic retain cycle checker that creates tasks for them. So that the tool finds the issues and sends them the task, and then, well, they need to see how to break the cycle and how to check that the cycle is not there anymore. So a bit harder maybe because also a context switch than when they're just developing the code. If they see the cycle right there, and it's easier.
And do you think this kind of analysis could also work at IDE time?
Yes. So at the moment, it will need to be fast enough running the analysis with all the dependencies needed to be fast enough for the IDE. But I think, yeah, if we make it a bit faster, that will be fine.
Okay, no more questions. I think we will stop there. Thank you very much.
Thank you.
We'll take a short break just to start at the right time in case people, yes. Okay, so it's time to start with the next speaker. Julien Van Egg, please.
Thank you, David. Hello, everybody. My name is Julien Van Egg. I'm with Bloomberg and Imperial College, and I will talk to you about how I started using Infer and at Bloomberg, particularly to find security bugs. And not only using Infer, but also I was very interested in actually extending Infer for new properties. So I will tell you a little bit about my experience there. All right. First of all, I really want to say I want to thank the Infer team because Infer is an amazing framework. Infer has separation logic. It has now incorrectness logic with the pulse checker that was talked about a little bit previously, and also it's written in OCaml, which is a functional programming language, a modular programming language, meaning that when you change Infer somewhere, you don't break everything else around, which is unfortunately very rare in the other frameworks I've been actually using. And so there are two, as you all know, there are two main kind of classes of properties that one may actually want to check in a program. One class of property is what most people actually are interested in is safety. And safety basically means that something that's wrong will never happen. You also have liveness. Liveness is something good will eventually happen. So, of course, in safety, you have all sorts of safety property you may want to check in programs. For example, the absence of array out-of-bound accesses, absence of use after free, absence of memory leak, etc. Liveness, a very famous liveness property is whether your program terminate or whether your program will do something that is desirable again and again in the future. For example, acquiring and releasing locks and things like that. And when you look at Infer, you see that a lot of the properties are mostly safety properties. So all of those that are have been talked about in the past are about safety. So one of the first question I want to ask the Infer team is, where did you put the liveness checker? And we'll talk about that a little bit today, because part of this talk is to report on a new checker I've implemented in Infer called Pulse Infinite, which is a checker that extends Pulse to find non-termination bugs in C and C++ programs. And why is non-termination analysis important? Well, first of all, if you look at the CVE database, you realize that there are tons of non-termination bugs out there, but there is no clear non-termination bug finder. There are tons of programs, tons of analyzers that are trying to prove termination, and some of them also try to prove non-termination. However, what Infer and Pulse allows us to do here is to have an under-approximate non-termination checker, which is not quite out there yet. And so what's really interesting as well when you look at those non-termination bugs is that they affect all programming languages. It's C, C++, it's Java, it's Python, it's Rust, it's, you get it. And it affects also very, very mainstream programs like the Linux kernel, OpenSSL. Many of them actually have no non-termination bugs in the past few years. So that makes it really relevant for someone like me to actually go after those bugs as we getting into the memory safety realm or the memory safe programming. We realize that non-termination is still a major issue that people have to take care of, and this is actually a little bit appreciated sometimes. Not only that, not only those bugs are present in a lot of different programming languages or programs written in a variety of programming languages, but also the trend is going up. If you track the non-termination issues, like the infinite behaviors in programs since 1999, thanks to the CVE database of MITRE, you realize that these keep going up. And so, as we, even this year we found, by we, I mean the community found about 60 bugs already, which is pretty much almost as much as last year at the end of the year. So people keep finding more and more non-termination bugs, but they get lucky. They find those bugs by getting lucky. Maybe the user actually discovered one such bug, but there's no systematic tool that can be used at the very large scale to find these kind of bugs. And that's where, that brings me to the core of my talk, which is really how can you actually use pulse and infer to find non-termination bugs. And we created this new program logic called Infer, which stands for Under Approximate Termination Analysis, with work with Azalea Rad and Peter O'Hearn. And I'm happy to report that it's now accepted at OOPS-Lab 2024 with minor revisions. And just very briefly, how that logic looks like. Just going to mention a few rules here. We introduced this new notion of infinite triple, right? Where we able to actually have a similar like OR style logic, except it's under approximate, so I should say it's incorrectness style logic here, dedicated to finding divergence bugs. For example, the sequential rule at the very top, say you have a couple of code fragments, C1 and C2. The first one goes from P to Q, and the second goes from Q to a divergence. Then obviously, if you sequentially compose C1 and C2, then that diverges. If you have a choice, say an if-else, a conditional behavior, and you know that one of the if or the else actually diverge, then you know that the entire conditional diverge is a diff choice rule. Similarly, if you have a loop, that's an interesting one. Or a repetition, it's really a repetition rule here. Say you have a piece of code C, it goes from P to Q, but Q is inside P, meaning that the set of state that you discovered is a subset of the state that you started with. Then repeating that piece of code diverge. And finally, if you have a while loop, the while loop while BC. So you have the piece of code C that goes from P and B to Q and B, and again Q is inside P, then putting that piece of code C in a loop guarded by the Boolean or the predicate B diverges. Yes?
What if Q is false?
Yes, what if Q is false? It's a good question, because if Q is false, actually that's a valid under approximation, and the premise is actually still true, that wouldn't diverge. Good point. Any other embarrassing question? So, by the way, I just came from New York yesterday, so if I fall asleep before you, that's why. All right. And so, just this small tool that we created, Pulse Infinite, based on the wonderful work of all the meta team over here. We've actually evaluated this on a few million lines of code so far, and we found 21 bugs. And when I say 21 bugs here, I'm not including false positive or anything like that. Our signals ratio is around 30% at this stage, but we're working very hard to actually make it better than that. So we were able to find quite a number of issues, and we reported those issues so that the community can benefit from our work. A few examples. OpenSSL, you have this function called AES-ECB cipher. You have this function, this loop on line 10. You can see what it does is that it iterates over an input buffer, and it goes from BL to BL bytes. The problem is, if the context is null in the call of EVP ciphers context OpenSSL get block size on line 5, then BL will be 0. If you do plus equals 0, of course, the root does not make progress, and you have an infinite behavior. Another example in libxml, you have a dictionary, right? The old entry, those variables are initialized as such. As you can see, you have this old entry pointing to the beginning of the dictionary table, and then old end pointing at the end of that table. Well, you have these conditions kind of bizarre on line 9. If that's true, the old entry gets reset to the original value. So you can see that if this condition is ever entered on line 9 and 10, then the loop is going to come back to the original state. So when I reported this bug to the libxml folks, what they told me, oh, but this condition is never entered. it's dead code. Like, well, if it's dead code, you should probably remove those lines then. Yet another bug in CryptoPP. CryptoPP is a small C++ cryptographic library, and it has wrappers for dynamic memory allocations in this aligned allocate, and that's quite a common actually source of infinity or divergence. It keeps trying. If malloc fails, it keeps trying forever. That's what I'm suggesting as a fix here is to have a counter. And if that counter reaches a certain threshold, then you should actually stop and say, you know what, there's no more memory, it's pointless to actually continue, we just want to exit the program. All right. Interestingly, when Peter O'Hearn actually provided this piece of code to LLM, the LLM was able to find the bug as well. Pretty interesting. All right. This is a little small, so I apologize for this. This is so we talked about the what, we talked about the result. Now I want to talk about the how a little bit, and I want to pass a few minutes on this. And I realize I'm glad I'm actually presenting this to realize how small that actually appears on the screen. And if you look at the implementation, how this Pulse Infinite tool is actually implemented, it's implemented as such. First of all, there is a little extension. There are a number of different component in Pulse. You have the main Pulse, of course, the main Pulse file, PulseML. You have the abstract interpreter.ml, which is colloquially referred to as Infer.ai. Then you do have the Pulse formula, which is a solver in Pulse. Okay, like Jules mentioned previously, was really it's kind of an SMT solver without using an SMT solver. It's very, very fast. And then you have the Pulse execution domain, which is some core part of Pulse where the Pulse state, or it's not called Pulse state in the code, but I just renamed it as such for clarity, where those Pulse states, the types of Pulse state are actually tracked. So let's go through a little example. I have a pointer here. No. Okay, great. I'm sorry. That's what happens when you actually click on buttons you don't know about. All right. So here I can actually read it properly. Here's how it works. First of all, whenever you have one of those prune seal instruction, that prune seal instruction leads to a call to prune binup in the Pulse formula part of the code. That Pulse binup, you can see on the top here, what it does is that it takes the path condition and then it adds a condition that the prune actually just send it, and just add these to the path condition typically, which is part of the domain of Pulse by default. One of the things that I added there is to make sure that that condition, this particular condition that we extracted from a conditional or from the loop predicate, is actually not optimized in the Pulse solver. And I'm going to show a bit later why, when this can happen and why this is a problem. But this is really important that this particular condition is not optimized out. The reason for this is because we want to be able to find those cycles, right, in those lasso properties, as we call them, when, on our small example here, when you have, say, a small loop while x is smaller than max, if x is different than 100, x plus plus. Well, obviously, this is going to iterate a number of times, but when it reaches the state where x equals 100, it's not going to increment x. That's just a toy example to explain. And then what this results into is a state space where you get into a state where x equals 100 and you just have a loop on that state. So it gets to an infinite diverging behavior, right? And so for every instruction, we're going to have this exec instruction on the very top left here. And for certain kinds of instructions, say the if and the while, it will actually call into this prune binup. So all good, we collect a bunch of constraints and we add this to the Pulse state. Then, for every loop, we're using the widening primitive of Infer AI to do something fun. So, as it was mentioned in the previous talks, the widening of Infer AI can be abused, and it is abused by Pulse to be under-approximate rather than over-approximate, as you would expect for an abstract interpretation framework. And so what we do here is, in fact, we do a k-bounded unrolling of the loop instead of actually trying to accelerate convergence as you would normally do with a widening operator. And so what happens there is that the widening, we added these transfer functions, let's call it like that, package, and that package is implemented in this execution domain. What package does is simply that it computes a work set. The work set is computed over there as just the new states in the pose that are not already present in the pre. So for every new state that have been created, we want to detect a lasso. Lasso as a cowboy lasso when you're going to, like, you're looking into, like, to catch a goat or something, and then you, like, bring a lasso around the neck as it's running, and then we want to find this lasso in the state space, meaning that we came back on a state we've already seen before. So we compute this work set, and then for every state of the work set, we try to see if any of the state was actually already known. And the way we do this is to having this hash table we call a widening state, or widening state, and that hash table is actually indexed by a triple. The triple is the raw equations that we collected through our prune collection on the top here, then the path condition of which was already there in Pulse, and finally the location of the loop. So for every loop in the program, we index the widening state through a path condition and the raw equations. If that index was already in the widening state, it means that we already found a state that was equivalent, at least according to those parameters, to what we've already seen before. And then what we do is we create a new state infinite program, which we added to the list of types of states that Pulse has. And if it's not, then we simply add the state into the widening state at this index, and then we try to detect the lasso on the tail of the rest of the work set. So that's roughly how it works, omitting tons of implementation details, of course, but it's basically how that works in Pulse Infinite. Any questions?
I guess kind of an implementation detail question. When you're extending Pulse in this way, do you kind of have to modify it, or are there ways where it's designed to be extensible, say, to track these raw, the raw EQs information in the formula and that kind of thing?
I had to modify Pulse in about 150 files. So, to answer your question very shortly, if we had a mechanism that could allow us, of course, to extend Pulse without changing the core of the code, that would be great. I don't think such a mechanism exists at this stage.
So here in your work sets, you keep track you don't keep track of the shape of the memory, or like a lot of the state of Pulse is gone at this point. So it doesn't really implement the rule you showed earlier, right?
It's slightly different in how the rules are implemented, which means that the rules are actually only covering the variables appearing in control predicates. Okay, let's keep going. So we're getting to next section of my talk, which is my laundry list of features I'd like to see in Infer. And so that's quite interesting because that is driven by a very concrete application of Pulse on very large code base, which I typically see is leading to either unsoundness or incompleteness of the analysis, particularly in this new checker. But I have a hunch that this is actually a problem for more than me. First of all, the Pulse optimization can hide bugs if you're not careful, which motivated some of my changes there. So let's see this small example. if you have a very basic loop that do not terminate, say int x equal 1 while x different than 3, y plus plus, obviously x will never be equal 3. And so you have an infinite loop in this particular case. You would like to see this bug. However, Pulse is smart enough that it recognizes that x is always equal to 1. And so it optimizes this by saying while 1 different than 3 instead of x different than 3. And it further optimizes this by true. And so, in fact, the way it means that there is pretty much an empty path condition that is being tracked there. And therefore, the cycle can goes from an empty path condition to an empty path condition if you're not careful, because those conditions were optimized away. Which it's the point of my raw equations with the additional part that I added in the Pulse formula solver is to make sure that those conditions do not get optimized away. So I can actually go from x different than 3 to back to x different than 3. Yes, there is a cycle in the state space which is not using an empty path condition. So if I have an empty path condition and I tell there is a bug, there's tons of false positive everywhere, so we can actually do that. And so it's very important to make sure that when you are detecting a recurring state using a logic like that, then those path conditions are not empty. And so those raw equations allow you to do this to make sure that when you are having loops that are, or even like conditional code that is maybe a bit trivial sometimes, then you don't actually optimize away those conditions. And this is part of my branch. Another part that I would like to do in the future is to detect non-termination bugs in recursive functions. Right now we don't actually support that, and there's a number of CVEs, like publicly known vulnerabilities that are actually non-termination bugs due to recursive function or uncontrolled recursive functions. One of them is in sklearn, which is extremely popular machine learning framework in Python. And so we would love to see a better support for recursive function. I've seen some movement recently by some guy called Jay Villar, where possibly the recent improvements of recursive function support will help us do that. To my knowledge, and I haven't really taken a look in very deep detail to these changes, it doesn't really try to detect a recurring state here. It's just more of a syntactic kind of like hint, right? So there's more to do there, but this is going in a good direction, where in the future we can imagine that we'll also support these kind of non-termination bugs as well. Yes.
My question is about the previous slide. I'm confused because I would think that if now the example is while true do something, you would like to catch it with your analysis?
So yes, however, the way that it works is that the path condition in the Pulse state gets set to empty. And so that goes from empty to empty when you actually optimize out those conditions. Because then you have no constraint to track. If you say, oh, it's true, then I'm just removing that constraint from the path condition.
But it means that now currently with your prototype, you will not catch infinite loop like while true do something? Because
there are a couple different modes in the tool. One mode is more noisy, where I find those bugs, but then that leads to a bunch of false positives. So I have another mode that remove those trivial lassos, as we call them, and then we don't find those bugs, but then the signals ratio is much better.
Yeah, about that, I was wondering what kind of false positives do you get in those? What's wrong about these empty path conditions?
Oh, yes. If you actually, well, it's those trivial lassos, right? If you start saying, oh, I'm going from a state that has an empty path condition to another state that has an empty path condition, therefore infinite loop, that's not quite accurate in Pulse.
But like in practice, what kind of false positives does that give?
I would have to look through.
Okay.
Sorry, at a higher level question, what parts of Pulse do you most benefit from in this analysis? Like, is it the pruning of infeasible paths that's built in, or is it the memory analysis, or why was it good to build on top of Pulse, like this analysis?
Great question. The two major bonuses when you're using Infer and Pulse generally, it has separation logic in it, and it has incorrectness logic in it. So you can do path dropping, right, under approximation, and also you have a very precise memory model based on separation logic that allows you to not make any approximation on that. So this is really, to me, one of the key reasons why I like Pulse a lot is because of that. The third version, also the third reason, is because it's in OCaml. The fact that it's actually written in OCaml, at least to me, is an advantage. For having actually developed a number of static analysis tools in C++ in the past, you're really like, you know, killing you, like banging your head on the wall when you have a bug. Well, those bugs in Pulse, well, when you get to the point where your code compiles, then you have a really good hunch on the fact that your code is actually going to work. It's not always the case, but it gives you such a huge heads up. Okay, another really great improvement I like to see in Pulse is the ability to reason about bit vector arithmetic. or generally, not talking about bit vectors, since like being told no, it's just the ability to reason about bounded arithmetic, right? Not necessarily bit vector, like bit precise, but if you could reason about bounded arithmetic, you would avoid incompleteness and unsoundness. So let's look at those examples. I have a very basic stuff where you know, I have false negative or false positive in a termination analysis because of the absence of that. Top example, you have int I equal, you know, max u int, and then while I is different than 0, I minus equal to. Well, because you're unable to reason about either integer overflow or integer underflow, then you will actually not actually you will not actually find. I'm sorry, it's mislabeled. Should be the other way around. But the absence of support for integer overflows and underflow really leads to missing bugs and also sometimes giving false positive. So let's look at the other one here. This is a false positive example where you have this condition while y is bigger than max int y plus plus y minus minus. So just looking at that code, you would think, oh, of course, it's going to not terminate. But in fact, this while loop is never entered because y can never be bigger than that. Y is an integer, a signed integer. Right? So this signed integer, int y, this while y is bigger than max int is always false. So you can't enter that loop. However, without actually having knowledge of that, it will think that you can enter the loop. Yes.
Okay. Yeah. So that false positive. I mean, why would you write that code? Did you see that in
It's
practice?
a example to actually show the behavior. But I've seen this behavior in real code. Absolutely.
Okay.
As a matter of fact, crypto code has a lot of that.
Mm.
In cryptographic code, you see a lot of bit level arithmetic, and that totally happens, stuff like that.
And in the first example, it's not about modular arithmetic, right? It's you're decreasing an odd number by increments of 2, so you never hit 0.
So I'm sorry, because this example is actually wrong. So so say I plus plus instead of I minus equal to, right? See if
No, but I think that's also an infinite loop, no?
No, because then your integer is going to wrap. It's going to go to 0.
Then it's going to be... No, it's still going to be odd. It's going to stay odd forever, no?
So remove. So as I mentioned, this example has a little bug in it. It should be I plus plus instead of I minus equal to.
Fine.
So if you put I plus plus in there, because you're using a rational solver, it's going to keep thinking, oh, you know, it keeps growing, and so that's fine. But in fact, in fact, if you add 1 to max uint, it's going to go back to 0, and then the loop is going to break.
Cool, thank you.
Yeah. Okay. So this is probably one of the top, I want to say the top 2 or top 3 reasons, of sources of imprecision in Pulse. And I realize that there may be a performance penalty adding support to this. The truth is, what is the real performance penalty? Because this leads to unsoundness and incompleteness of not only the non-termination checking, but on any checker that you would actually want to actually spot integer overflow, underflow behaviors, which is present a lot in security bugs. You see a lot of those, and the fact that Pulse does not support this is a problem. All right. So I want to ask, is somebody at Meta taking care of this thing? Because it's not a small job, first of all. I recognize that it's not actually a small job to add this. However, this is a needed feature. And we would like to use that feature whenever that becomes available. All right, what are the future plans? We want to do a larger scale evaluation with Pulse and Infer, obviously. We started analyzing the Linux kernel and the Wireshark. One of the things I actually failed to mention when I showed my evaluation is how amazing performance is with Pulse. Look at those at this analysis time. You're talking about analyzing 1.5 million lines of code in about a minute. It's very, very fast. And I take no credit for this. I think actually Pulse does it all for me. But the point of this is to show that I'm not actually degrading performance of Pulse. But it's really, really fast, and it's amazing that it's so fast because it's very scalable and it can be plugged into the CI/CD pipeline easily. And so, coming back all the way, we want to do a larger scale evaluation. The Linux kernel, when I analyze it, it's about 26 million lines of code, and it took 18 minutes to analyze. Super fast, super usable, great. Wireshark, it's about 5 or 6 million lines of code. Also, would love to be able to, review very efficiently the results there. And so there may be some new feature we want to add to combine this with non-termination. For example, there is an initial taint analysis support in Pulse. If we mix the taint analysis with non-termination, we could find not only non-termination issues, but non-termination that is induced by the user. And in terms of criticality, that goes to the top of your list, right? Because, the user can provide me a value that is going to lead to a non-terminating state or recurring state. Well, that's really good. If you find a bug like that, everybody's going to fix it very, 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 very fast. Of course, we want to keep tracking false positives or false negatives. It's really important when you are using a tool at the very large scale, when you're dealing with tens of millions, hundreds of millions line of code. Even if you have a tiny source of false positive, be sure that this source of false positive is going to explode at the very large scale. So tracking every single source of false positive is really, really important when you aim at actually deploying a tool like that to hundreds of millions of line of code. And finally, once to the point where we are extremely good at signals ratio, we're not 30% or even not 50%, but we're more like 80%, we want to start adding more detection logic where we don't want to compromise on the number of false positives, but we want to find more and more bugs. So that's what we're going to do in the future. Thank you very much. I'd like to thank Peter Ohon and Azal Erad and Jules Villard for their guidance and collaboration. You can actually check out my code. It's open source on GitHub, and you can contact me with any questions. Thank you.
Hi, this is really cool. So you can have denial of service attacks in cases where the behavior is, doubly exponential in the size of the input, but not non-terminating. Is that like a giant gap between what you're doing and detecting cases like that, or is there hope of some kind of extension to your technique to detect you know, those kind of explosions that might also lead to CVEs.
You're totally right. These bugs actually exist, and there's a number of tools already finding those bugs. For example, the work of Caroline Lemieux, she's actually doing some of that with fuzzing, or trying to find, like, you know, regular expression code that actually has exponentially increasing complexity that lead to not to non-termination, but that leads to like a almost non-terminating behavior. We're not finding that. We actually leaving it to her. So it's kind of a different. It's a different property. I would argue. Yeah.
You mentioned you found 21 non-termination bugs. So how many of these were security issues, to come back to the title of your talk?
It's hard to say without writing, say, proof of concept exploits. However, some of them were exposed through the outside, some of them were not. So it's a mixed bag. But I did not attempt at writing exploits against these bugs.
Did you file any CVEs?
I'm waiting for these bugs to be fixed before claiming CVEs. But I reported the bugs.
Yeah, did you find examples of errors where you needed the interprocedural part of the analysis?
Yes, absolutely. For example, this OpenSSL bug, right, requires interprocedural analysis. If you don't actually have, if you don't realize that if context is null, then it returns BL equals 0, then you can't find that.
And my other question was so about the back test. I mean, in the implementation, when you try to recognize that you have already encountered a pass condition, I'm surprised that you can you do a kind of equality test between pass conditions, and I was does it make sense to do an entailment test, so that something is already implied but what you have seen or something?
Absolutely, it would make a lot of sense to do this, and you find more bugs if you did that. So one thing to remember is that the path condition being optimized along the way by the pulse formula solver sometimes gets simplified a lot, and so the path condition is not sufficient. You have to combine this with raw equations of your predicates along your path, which is not the same as the path condition in pulse because of these optimizations. This said, if there was a way to actually do entailment checking in pulse, I would absolutely use it. After talking to Julie, you mentioned that there's no such thing. However, there is a LEC primitive for states that can be used. So that would be great if I could actually use a facility to just check whether a P implies Q. But I don't think there is such a thing, unless, please correct me if I'm wrong.
Thank you for the nice talk. I have a question about when you asked for support from Pulse for the bit logic. I wonder if what it take for Pulse to support that, and can any of these rules be implemented by you as a user of Pulse to handle this bit logic? And given I am not given
trying to put more work on me, huh? We're in discussion with the Infer team to see how whether or not we have a way forward with that, because it's not a trivial amount of work. This said, there could be simple ways to get most of the behaviors that we're looking for without implementing a whole bit vector arithmetic solver. So let's call it work in progress or brainstorming progress.
Thank you.
Any last question? No? Well, thanks again for your time, and find me in the corridor.
already. So welcome for the afternoon session. The first talk will be given by Nikos Gorogiannis. I explicitly asked Nikos to give a talk about this topic because I think it's something that is not very well known outside of Meta, and we have a lot of papers about Infer, some papers about Infer, but these details are not so well known. So it's great that Nikos accepted to do this talk, and that's yours. Thank you.
Thanks. Okay, so, but you could hear me anyway, right? Sure. It was the secret stuff. So yeah, so this is more about how one might. So if someone wants to run Infer on a large code base, in a continuous integration system, then you might want to know about certain things and also understand how some things are designed in Infer, so that you can get the most out of it. So that's the kind of overall idea here. So I'll first talk about what probably most people who have used Infer know already, the basic phases of a run. Then I'll go into a few things, a very high level overview of capture and how the integrations work at a sort of abstract way, and how one might parallelize more capture as applied to their situation. Then look at the analysis where, as we've already heard, especially from Jules, how the on-demand analysis works. It was very, I think what Jules didn't have a lot of time to go into is how do we parallelize that bit and the various different options that exist today to do that. Following on from that, so that's already something that exists in Infer, and you can control that when you run your experiments and so on. But the next level up is how do we distribute that analysis over several hosts, not just one that has multiple CPUs or cores, but over a larger, a set of hosts if your analysis needs go there. And then how we can get better, better performance in doing that by being intelligent in how we partition the work that we distribute. So that probably everyone, like I was saying earlier, probably most people might be familiar. This is the sort of basic flow that you have. You have some, it's assumed that you have some build system, your code base has some build system, right? Or it's maybe just a compiler that you run. Here I've written modified files, but really that should mean maybe a subset of the files that your code base consists in are of interest to you. Maybe you don't want to analyze everything in your code base, so maybe that's a commit. So you only want to analyze starting from a small set of files and then branch out as needed. And the first thing that will happen is what we call capture, which is really the equivalent to compilation. or building your code, but here it means that Infer plugs into that and gets all the SIL and CFGs out and stores it into its own databases, so it can then consume it during analysis, which is where the magic happens. And then finally that outputs procedure summaries and error logs, which are here separated just for the purpose of making it clear that essentially when Infer runs the analysis, the summaries are produced and also consumed because of compositionality. But we also generate logs of what are the errors that are found, and then these are consumed by the phase that takes all that and then produces error messages, traces, and so on and so forth. Typically, analysis and reporting are done in one step currently, and you actually have to, so by default, reporting happens automatically after you do the analysis. You can stop that if you want. There are flags for everything, but that's the main flow. Okay, so capture here, obviously it depends. Okay, obviously it depends on the language that you have, that your code base is in, but it also depends on the build integration that your code base has, right? So you could have just a plain compilation command, and that should, by the way, these commands here make it clear that we're only running that particular phase, right? So we're only doing capture, we're not doing analysis or reporting or any of that stuff, right? And yeah, so if you were after a few files in C, then you might do this, and that will make Infer use a particular integration that's adapted to Clang and run its plugin, etc., etc. So it's a very, it's a language and integration dependent flow. Similarly, with this would work for compiling a Java file. And I've included that actually because I know that loads of people have been asking, oh, I have a jar file or I have a class file. I have already built that bytecode, and because Infer actually consumes bytecode, doesn't really consume Java source code, contrary to what the Clang integration does. This is how you might capture that bytecode directly if you were in that case. Anyway, the point is that these three are, let's say, the root integrations that are very language dependent, and on top of those, you would have integrations that run some build system, and then Infer has to plug into that by in various ways. In the make integration, what it does, for example, is that it pretends it is the actual compiler. So when make runs, instead of running Clang, let's say, it would run effectively a version of Infer that is standing in for Clang, and then Infer would produce the same sort of side effects that Clang would do by also running Clang, but also it would get all the flags it needs to run its own capture directly. And there are other integrations like Buck, Gradle, Maven, etc., that exist in the Infer repository, aren't all used by us and maintained by us, but yeah, and it's possible to write more. Yeah, that's more or less the gist. Okay, now this is what, so if you, let's say you have some build system, but you have a large code base, or you want to integrate in your CI, and your particular build system, when combined with Infer, leads to poor execution times. What can you do? You could just say, okay, I give up, or this is how it is. So the problem is that the when you use the build system, let's say we have make here. Essentially, this is a dependency graph of the targets that your build system might have. Essentially, the parallelism here is bounded by the build system itself, right? So you cannot have more infers running concurrently than, let's say, 2 for this graph, because that's the width of this graph, right? So the build system forces the leaves to be built first, and then it crawls up, it climbs up the graph, right? And that might make sense when you're doing compilation, but it doesn't necessarily make sense when you're capturing with Infer, because really you're not going to be building a binary here, right? So you don't need necessarily this dependency structure. What you want is just to syntactically consume all the source files, right? So in this case, using the build system might be a bit counterproductive in terms of how long it takes to run the capture. And so the idea is that if you can break down this, let's say, per individual target, and that, okay, there's a bit of an asterisk here, because the idea is that that assumes that each of these targets is buildable without the dependencies necessarily being there. Okay, so this is a bit tricky, but let's say we had some graph that we could cleanly chop up into more subsets. Then we could do the capture individually in each of these sets, and then merge the results all together, which is so all this could be done in parallel, whereas this is a very relatively fast sequential step, right? So yeah, so that would mean you could capture all these in parallel, like I said, and then do the merge. The buck and Gradle integrations in Infer are written exactly using this technique. So for example, the Gradle, it will do some magic by running Gradle itself and then consuming its debug output. But then essentially what it will do is that it will recompile all the files, all the Java files, using the commands it has found in the debug log. But it will use the Java-C, essentially this line here for each one of the files, right? And all these can be parallelized, right? There's no dependency necessary, structure necessary here. So they will all be built essentially in parallel and then merged into one capture database at the end. Yeah?
Could you detail what you mean by merge?
Right, yeah. That's a good point. So merge means so here, this is the output directory of each command, right? So we build, let's say, n targets. We end up with n output directories. And each output directory has a capture database inside. It's all SQLite. The capture databases contain CFGs and type environment information, essentially, and source file information. And all these will be essentially unioned into one database with this command that will end up in this output directory. And there are some subtleties about what happens when you have duplicate occurrences of procedure names or file names, and the this algorithm that does the merge has some logic where it won't just blindly overwrite one duplicate with another, but it will try to make sure that any structured information contained in there will be unioned essentially into the final database. Okay, let's go to the perhaps more interesting parts, which is the analysis. So here, okay, so here we have some files to analyze, right? So again, I remind people that we don't have to, when we capture a code base, we don't have to always analyze all of it. We can be we can have a narrow targeting of the files that we want to analyze. So here we have some sets of files. We give it to the scheduler, and the scheduler will do its thing and essentially prepare some partition, do some, let's say, distribution of work, computation into work packets, and it will start concurrent processes that each one will do analysis, and it will then distribute the work packets accordingly. That's just standard parallelization. And here I've just put the capture DB that is being read by the workers and the analysis database that is being read and written to to write summaries and so on, and error logs. So currently there are 3 schedulers available. I'll go through them in the next slides. And you can control the number of workers. Yeah, and that's the kind of high-level picture here. So the file scheduler, which was the first scheduler that ever existed, and in fact it wasn't even called a scheduler back then because it was kind of the way it was done, essentially takes as a work packet every source file that is in the set of files to analyze, right? So and what it does, so each file gets sent to one worker, right? So here we have 2 files, and the worker essentially reads the list of procedures in every file and then says, okay, let's analyze each procedure at a time, right? Sequentially within each worker until I finish, right? That's the very basic stuff. One funny thing about it is that it allows races over summaries, right? So let's say we have scheduled here these 2 procedures in red. That's a common dependency of both of them, transitively speaking, right? And if timing is, if the timing constraints are just right, then both workers will end up analyzing the same procedure concurrently and even write the summary twice, right? This isn't too bad in terms of correctness, because most of the time we're deterministic, so we should write the same summary, Here, as even though we may do that several times, but it's not great in terms of worked application and parallelization of work, because we're basically, if we could have done it in one worker, then why do it in several, right? And there have been we have observed pathological cases where, especially when where multiple workers would go down a very long chain and race all along the chain, right? So they wouldn't just be one summary that they race on, but a whole, or dependency graph, in fact, right? A whole cone of procedures that they would race and duplicate all that work. So, so that's one deficiency or one disadvantage. The advantage is that it's a very simple one, right? So, there's advantages in simplicity. The other disadvantage that for some use cases, that the granularity is coarse, right? So your work packets are the files that you want to analyze. So if you have very few files that you want to analyze, that's your maximum parallelism, right? So you can't go any faster than that, any more parallel than that. So if it's in a CI, for example, if it's in a continuous integration system where your commits have 1 or 2 modified files and you start from those files, then you're not going to buy a lot of performance like that. So, yeah.
Is it possible that 2 workers are working on the same file?
No, but they might work on the same procedure that is, so, okay, so this is why I've put this upward arrow here, right? So you, actually you could even have, yeah, so the arrows can be anywhere, right? So you could have this worker working on that procedure and this worker working on that procedure, right? But they wouldn't have the same work packet, right? Each file as a file goes on to one worker only, if that makes sense. Okay, so then the first step we took was to to use the static call graph in order to partition the work at the level of procedures and not files. Okay, so what we do here is that we go through the static call graph. We build the static call graph. And what is the static call graph? Is basically what I mean by static call is the calls that are non-virtual. They are explicitly in the CFG of each procedure. Okay, so we read those and we construct the static call graph. Okay, here I've used dotted lines to represent the dynamic dependency or real analysis dependency, and the solid lines to indicate the static call being present in the code. And once we do that, we can say, okay, I'm going to take all the leaves. I'm going to schedule them first, right? The leaves meaning they have no dependencies that are not summarized, let's say. Right? I'm going to analyze these first, the procedures in red. And when I'm done, I'm going to climb the graph gradually until I'm at the top, right? And because these procedures, well, first of all, they are procedures, they're not files, so the granularity is much smaller. We're going to have loads of them. And it's a frontier that will climb the graph, so the width can be high and we can get better parallelism, so that would help with performance. But there is the problem of dynamic dependencies. What do the dynamic, so does that affect soundness? Well, no, because we're still using the same on-demand analysis, right? So if we are asked to analyze this procedure, we will necessarily analyze that as a dynamically, as a dynamic dependency, right? It's just not going to be in the static goal graph, so we're not going to be any wiser in terms of performance scheduling, right? So that's one issue here with the dynamic dependency graph. It does reduce races, right? Because of the way we climb the graph. If there was no divergence at all between dynamic and static, then there wouldn't really be any races, right? Because we would always be scheduling distinct procedures that have no dependencies, right? And that means we should never send the same procedure to 2 workers, right? However, when there are dynamic edges, and they do exist a lot, and I should add, because I think we haven't mentioned this up to this point, it's not just calls, it's also whatever any analyzer may treat as a dependency, right? So examples are, so for example, the deadlock detector would say, okay, I see I'm locking here a lock that is stored in some class A. I will go and also retrieve all the summaries of the methods of A to see if there's any deadlock, right? Which means that essentially we have edges inserted to all the methods of A where there are no static calls in this current procedure that I'm looking at. Okay, so it's not just calls, it's anything an analyzer might request as a dependency. And so these are even more of, they occur even more often than just dynamic or virtual calls. Okay, and what happens with cycles? Well, because if we have a cycle, obviously, that's never going to have any leaves inside it, right? So how do we analyze the cycles? We basically leave them for the end, and then it's as if we were using the file scheduler to go through them, right? So we just fall back on the stuff in the previous slide for the cycles. Yeah?
Yeah, I have a question about the static call graph. So you just take into account static calls. You don't try to over-approximate virtual calls by type informations, because, for example, in Java, you see a virtual call to M, but in fact you see A.M, and maybe, so you know that there will be a subclass of A, where M, and sometimes it is A itself, so it's not bad to use it.
Yeah.
Maybe
so
it's not true, but it's not bad to take into account this type
so you're
proposal.
Saying where we have a static call, well,
where you have a virtual call, you could guess.
A virtual call, yeah. So I think in the current situation, it is treated as a static call to the static class to the static type that is seen in the. So we don't analyze the whole hierarchy, but we at least consider that as a call to the static type. Yeah, we could, but that would add potentially a lot of more edges here. I don't know whether that's, we've never tried that. Okay, and the last iteration on trying to build more performant schedulers was, let me just look at the time, okay. Is the restart scheduler, where the idea here is that we schedule at the level of procedures, so we have high granularity. We schedule the procedures in the files that we want to analyze, so we don't look at any graph. We don't do any pre-computation of the graph. So here I've put, let's say we have just these two procedures to analyze. So we start analysis from those, and every worker will take one of these, and then we'll start an on-demand analysis as usual. But what happens is that when a worker starts analyzing a procedure, it will put a lock on it until it has finished writing its summary, and that's when it will unlock it. So what happens is that, let's say this worker starts, it will lock this procedure. It sees that it has a dependency on this procedure. It will go down, it will take a lock on that procedure as well. Okay, so these two have been locked. And meanwhile, this other worker starts analyzing this procedure, locks it, goes down the graph, says, okay, I need more, goes here, and then it tries to lock, but then sees that the other worker has the lock. And what it will do at that point is that it will fail the whole work packet. It will pop essentially the whole call stack, unlocking along the way. And then when it goes back up here, it will give that work packet back to the scheduler and say, I failed to do this, please reschedule this and give me something else to work on. Okay? And the idea is that this eliminates essentially almost all the races. Theoretically, it completely eliminates the races, but practically there's some double-checked locking that we should do, and we don't because it's very poor performance. So we have, like, I don't know, a few procedures in the thousands raced on. So we don't have any more worked application because of the races. but essentially we have some worked application that happens in time, right? Because when we fail due to a race, we have done some work that will have to be redone the next time the worker will, the next time the same work packet is scheduled again, right? So every time a work packet is failed, some work gets lost because it wasn't written to disk, and therefore we have to redo it next time. And it may live lock with highly recursive code. Okay, so we have some, so if you imagine big cycles and two procedures on the cycle on opposite ends getting scheduled to different workers, right? So they might go around the cycle and then realize that both of them cannot progress, right? Because the other, well, it shouldn't happen that both of them do, but it might happen depending on the scheduling. So yeah, so we might have a lot of restarts essentially, and possibly even live log. There is some code to detect that, which is that basically when we send a work packet back to the scheduler, we say, okay, this is the summary I failed to take the lock of. So don't reschedule me until that has finished being analyzed, and that reduces to some degree the risk. Okay, so that's all about what happens in a single host when you're doing analysis. Now, how can you distribute analysis if you have a large code base that you know, one computer is not enough? Yeah, so one way is that you can do your capture, okay, get all the source files that were captured. Okay, so now I'm not gonna talk anymore about analyzing just a subset of files in your capture. I'm just gonna talk about analyzing everything, okay? And then split that list of files in as many sets as you have hosts. Okay, so just build a long list of source files and just partition them however you want into different sets. And then copy the capture database that you got to all the different hosts that you have. And then in each host, pretend that you're actually not analyzing all the files, but just the set that you got from your partition. Okay, so you run n analysis, one for each set, separately, but starting with the same capture database. Okay, so this is like a broadcast model where you copy the capture database to all the hosts, and then once you're done, you collect all the output, the result directories, and remember that reporting happens on every host. So reporting has happened already. We just need to merge the reports, and that's there is this extra machinery that you can use to just essentially JSON merging. You could do it by hand if you wanted. So that's a basic distribution model. Very kind of simple. The one disadvantage that you get with this is, again, worked application. This time, it's not exactly a race because we're not racing over the same data store, but you may end up analyzing the same procedure on multiple hosts because it is a transitive dependency of two files, let's say, and one file has gone into one host and the other file has gone onto another. Okay, so both hosts would then be obliged to analyze that same procedure twice. So for that reason, we have added some facility that can do the partitioning in a more intelligent way to reduce the worked application. So the idea here is that we're going to go to the static call graph, right, to do this more intelligently. And we are going to build a version of the static call graph, but on files, not on procedures. And the main reason for this is that we're using all the machinery we have. We're not really able to schedule specific, to ask for specific procedures currently. You know, this option, the changed files index option, really is a set of files. So we assume that the granularity will be at the set of files where you do your partition. And so therefore the static call graph will be at the level of files. Now, the lift to the file level is kind of trivial, right? But that's not necessarily going to lead to a good partition later on. So so here we have 3 files, okay? And I have drawn some dependency arcs. What happened is that if we lift in a trivial way this relation to files, then we're just going to end up with an arc here, an arc there, and an arc back. But this doesn't really represent how much work is entailed to cross these edges, if you like. You know, how much does this file need that file, all the summaries in that file? Okay, that's not captured if we just lift blindly. So what we do instead is that we put weights, and the weights are the number of distinct callees in the target whose summary I need in the source. Okay, so here everyone is calling, in this file, everyone is calling the same procedure, so the weight is going to be 1. Okay, and the idea of not counting the number of times, but rather the set of distinct callees is that because they're going to be cached anyway, and they're going to be analyzed just once, there's no point you know, counting their number, just counting the number of calls, but rather the number of distinct targets. So here the weight would be 1, here the weight would be 3 because we call 3 distinct, and the back arrow will just have a weight of 1. Okay, so we build all this graph, and then we, of course, we're going to end up with cycles, right? Because we lift up to file level. So the first thing we do is we make that acyclic by deleting minimal edges. And then we do a sort of spanning forest computation, again, by deleting minimal edges. And then essentially we have a set of trees, and we try to distribute these trees in the workers that we have. So each worker will end up with a set of trees to analyze. And then we do an extra step where we try to make sure that the resulting total number of files sent to each worker isn't too divergent across the set of workers, so we don't end up with one worker having to do everything and then all the others just analyzing a single file, because of course that would, you know, mean that the wall time would not benefit, right? If we have imbalance between work packets. So we do an extra step where if the imbalance is too great, we keep removing edges until from the largest trees until we can spread them sort of equally. Yeah, so this step here would be inserted essentially in this place, in this procedure, to do the partition more intelligently, and then the rest would work as is. Okay, and that's all for me.
Hi, thanks for the talk. So for the intelligence partition part, I'm thinking, is it possible to not partition the whole program by the physical file? I mean, you can make it like a virtual file, which is not really the procedures belongs to get a better edge between them. But I'm not sure if this will introduce another more difficult problem, like how to partition. So I'm not sure if this is a, have you guys tried that or something? Yeah.
No, it's a good point. So I think if we added infrastructure for selecting specific procedures to, when we start the analysis, can we tell Infer, I want not just this file, but this particular procedure in the file. If we did that, then this whole thing, I think, would just work out of the box, because the same algorithm will work for procedures, right? It's just that we will not have the weight information in the same way, right? I don't know how the. Yeah, and I don't know. It's a very heuristic issue, right? How to distribute the work. So it could be that it's a good approach, or it could be that it doesn't make a huge difference if already we have a large number of files. So if we distribute the files themselves, we end up, having a reasonable distribution at the end.
Mm-hmm. Yeah, I see. Thank you.
Yeah, I was wondering, so how much of this work is front-end independent? If someone write a new front-end, does he have something to configure, or is it just for free?
You mean this bit, or
all the infrastructure about capture analysis?
I mean, the front-end specific stuff is just this bit, right? So just this bit, in fact, right? Everything else is generic in at least the front end, and in fact, both the stuff about scheduling as well as distribution carry over. However, the efficacy will depend on aspects of the language. So as an example, dynamic languages mean, a highly dynamic language like Hack essentially means that the static call graph here is worthless, right? And that means this is as good as round robin partitioning or random shuffling, right? Which is, it's not terrible, but it's not great either. And that's also one aspect about the schedulers, right? It's the same idea here, is that if the static call graph is not very representative of the final result, then you're probably better off using the restart scheduler, and vice versa.
Okay, so maybe another one. And Infer is meant to be used as an incremental static analyzer. Any idea to use incrementality for the scheduling?
Yeah. Jules wrote this replay scheduler, right? I don't know why we don't use it, but so yeah, okay. So currently, when we write a summary, the summary includes the actual dependencies that were used to compute that summary, right? Because sure, we don't know these when we start analyzing a procedure, we don't know what this might be yet, right? We can only guess by the static call graph. But when we finish writing the summary, we know. We know the exact things we needed, right? So we do write that information in the summaries. And so we can reconstruct, after the analysis, we can reconstruct the true dependency graph, right? So if we were in a continuous integration system, we could say, okay, I'm not going to use the static call graph to schedule. I'm going to use the call graph scheduler, but I'm not going to use the static call graph to schedule my analysis. I'm going to use the last true, real dependency graph I got for these files the last time I analyzed them, right? Or some, approximation of that. So that might work a lot better, in fact, than the call graph scheduler as this now. But we haven't done that yet. And also, you mentioned incrementality. There is an incremental analysis feature in Infer, which I didn't talk about. And it will work. So if you have run an analysis and you immediately want to run an analysis on a slightly changed version of your code, there is a feature that will will do exactly this, use this idea of reading the true dependency graph and then trying to invalidate only the summaries that have, that are known to potentially have changed or to not, no, what's the right word? It will invalidate it will keep all the summaries we know for sure could not have changed. Let's put it this way.
Okay, thanks again, Nikos. So the next talk is in 3 minutes. Yes.
Is it already on?
Oh, that's for the clicker. It's this. Sorry, look at this.
Maybe presenter view, and this one I will move to you. I don't know why the mouse is moving slowly. Is it working?
I see. That's it. 40 meters. No, it's it saturates the workflow. There's only one writer. Why did you think that? How many readers still still need to know from which point to read, which point, or up to which point.
Okay, so it's time for the next talk by Matteo Marescotti.
Thank you. Yeah. Hi everyone, I'm Matteo, and today I'll talk about how we use static analysis data at WhatsApp to provide Infer with additional information to perform better and in some ways to supercharge Infer. So first of all, WhatsApp is one of the most used messaging application in the world. It's used every day by around 2 billion people, so that's a lot of people, and so these people use WhatsApp to exchange messages, and that means exchange a lot of data. And just to give a sense of how much data they exchange, this is the number of messages they exchange every day is around 100 billion. Like, it's actually a lower bound, so it's even more. And the data starts from clients, so phones, and end up in clients. But over the way, and it passes through a server, right? But the server is not a single entity. It's actually a set of microservices, so there are a lot of them. And they are divided in regions, so there are several around the world. And all of them exchange also data. So keeping track of where data goes, and also within the server is quite complicated, not only from clients to server, but also within the server. And what our team tries to answer is this question, like, no sensitive data flows exist from any source to any sink for a given set of sources and sinks that are provided as specifications. And I want to present to my team. So the work I'll be presenting here has been made possible by all these people, and we are the Privacy Cat, where CAT stands for Code Analysis Tool, unfortunately, but yeah, the logo shows instead a cat. It's cooler. So I said that we try to answer this problem, to face this problem with both static and dynamic analysis, and we do it with several tools, but the only static analysis tool we use for this purpose is Infer, and more specifically the Erlang integration. Yeah, Jules told. Oops. Oh, no, this is a problem. Okay. Yeah, sorry. Thank you. A mess.
Do you want to properly wipe it? You know, with this?
I think it's okay. Yeah.
You think so?
Yeah. Yeah, I think it's okay. Yeah.
There's a bit of water between the keyboards.
Yeah, but as long as it doesn't die, I don't want to touch the buttons.
This is here.
Okay, yeah.
We can fix the rest.
Sorry for the mess, yeah, okay. So I said that we have several tools to answer this question, and we use Infer. Yeah, this is the Erlang integration. So Erlang is one of the several languages that Infer understands, and it's yeah, it can check for reliability issues and also data flow properties. This is what we use it for. And we use several dynamic analysis systems instead. One of them is Fausta. This is the one we use as a source of input for this integration between static and dynamic. So this is the one I will cover more, but we have several others. For example, we have end-to-end tests that cover specific cases of interaction between client and server, and also Sapiens that simulates real touches in the interface and monitors what's happening in the clients and in the server. Fausta instead performs traffic generation, so it instantiates real packets of data that they look like this. They're called stanzas, and it creates a sandbox of the server, and it starts to move around these stanzas from clients, fake clients to servers, like in this sandbox. And the way these stanzas are generated is from a specification that is originally intended to be used on the server side for validation. But since they contain also the expected type of data, this is used by Fausta to create legit information. Like, for example, there the spec says that it expects an IP with port, so Fausta knows how to, Fausta knows that there should be an IP, so it creates an IP and sends the stanza. So the server does not reject this stanza and performs as if it was running in prod, basically. Instead, for static analysis, and we do data flow analysis using Tuple. Tuple is an engine inside Infer to do this data flow analysis, and the property has a form of a finite state automaton like the one on the bottom. It is capable of, like this finite state automaton represents a possible data flow from a source, a function called source, to a function called sink. And Infer knows how to move in this finite state automaton based on the function being called. For example, when there is a function called source, the return argument is stored in a variable called dirty that is carried over with the finite state automaton and in a new state, and then there is this loop, non-deterministic loop for all the other statements that are not relevant. And when there is a call to sync and the first argument happened to be dirty registered before, then the automaton goes to the error state and the flow from start to error inside Infer is the issue, so is the real issue that is reported at the end. So we have a problem here. The first problem is that if there is a complex function in the middle, then Infer is not capable of following through and transition to the error state, because complex functions are treated as by Infer as a non-deterministic function that return a non-deterministic value. So what happens in reality is that Infer don't know how to do, like, don't realize that argument is actually dirty, so it doesn't take this this transition. So the error is actually missed. And the second problem is, yeah, this is a slide on demand, like similar to the one Jules showed us this morning. So it's very similar. We have this function bed that calls another function complex. And what happens is that Infer try to compute the summary of complex, but because of its name, it's not possible to do. So it fails. And this is also used to compute the summary of bed. So if Infer fails to compute the summary of this function complex, then also doesn't produce a summary of bed. So there is this chain reaction that. So if there are several complex functions that have a lot of dependencies, we end up with limited coverage. Like by coverage, I mean summary functions with some summaries. And this is why initially we created the Erlang models. And Erlang models are ways to provide additional data to Infer, like additional on top of the source code, to substitute some of the functions with input-output pairs. It works well, and it is Erlang specific because Erlang functions are pure. So there is no state, and there is no global variables. It's some things make Erlang a bit better for this work. So you just provide input-output pairs. Once you know the arguments, you know the return values, and that's all you need. So yeah, the structures and input-output pairs and can be provided in JSON or in SQLite format. So these are, yeah, I'm also providing this slide, although the information is available in the manual, the Infer manual. This is how they are defined in JSON. Basically, there is a list of arguments. It is a list of Erlang values as for the argument, and the return is one only Erlang value. And the Erlang value can be an atom, and then the name, an integer, its value as a string, a list, so it's like a recursive type, like a list of Erlang values, or a tuple, it's similar to a list and treated similarly. And finally, there is this function value null that is used to represent non-deterministic values. So when null is provided, basically it always matches, and everything matches. So if it returns null, it means that it's non-deterministic, basically. Yes, this is important. Functions for which a model is provided are not analyzed. That means are completely skipped. Infer doesn't read the source code for these. It just relies on these input-output pairs, and during the search, if there is a matching between what is passed, then the respective return value is used. And if it collides with some assertion, then it is an error. Yeah. Coming back to what Fausta does on the dynamic side, yeah, Fausta is a complicated framework. I'm not gonna explain that picture. This is just to prove that it's complicated. It has a lot of squares. So but what it does, yes, it instantiates this sandbox, and it creates clients, and it makes clients connected with the server and exchange information. The interesting piece of this slide is the component down below. This is a built-in module of Erlang called DBG, and is the trace-based facility. It can be plugged into any Erlang system running. And what it does, it takes as input a list of Erlang functions, and it produces as output the traces that are arguments and return values for each call that happened during the execution. So this happened real time, and it writes them real time in like some Erlang format on some file. Yes, so basically by plugging in the text-based facility to Fausta, we are able in real time to get the arguments and return values of a list of functions while the server is running and while this information flows from client to server. So the missing piece to basically connect dynamic and static is the trace to model, right? We have the traces and we would like to have them as Erlang models so we can plug them in as we do, right? And this is the missing piece of this connection, and is this module trace to model. And it takes this GDB traces written that have a format that is Erlang specific and transforms them to JSON, basically, or to SQLite, depending on how many they are. The SQLite is easier because they can be indexed by name, and it's faster for Infer to fetch them while doing the analysis. This is the interesting part is that we use Fausta, and I will show experimental result using Fausta, but any Erlang system can be plugged into DBG. So also tests, Sapiens, everything, in general the server and any kind of dynamic analysis can be used. So it's not Fausta specific. So this is just how the translation is done. These are Erlang types and the respective Erlang model JSON produced. So atoms just become atom. Yeah, same for integer, list, and any type that is not in this list. Like for example, records. Yeah, so that there is some missing types that return null. So it means it's non-deterministic, and everything can, all the values will match. So this slide instead is an end-to-end example of how the big picture about everything. So we have this code with a simple function that increments an integer provided as input, and a complex function that transforms the input into string. This is performed by integer to list, since in Erlang strings are represented as list of characters. And suppose that this function is complex and Infer fails to analyze. When we call complex of 42 with GDB, the tracer, we basically get the input and output of both inc and complex. So, and it look like this. For the function inc, we get arguments 42 and return 43. And for the function complex, we get as input 42 and return a list consisting of the characters 4 and 3. Yeah, so 52 and 51. After trace to model consumes these traces, this basically, there is a list of only 2 because the function calls only once, but if there are more other calls, all of them will be recorded and will produce one of these JSON items on the list, and each of them represent a single specific call. So we also implemented abstraction because, as can be seen from here, every model is a specific input-output pair. And after running the server for a while, we get millions of these. And there are too many for Infer to consider one by one. And we implemented some abstraction. And it's a very initial implementation of abstraction. So basically, we keep a list of what we are interested in. And for all the rest, we just say it's non-deterministic. So for atoms, we keep a list of atoms that we're interested in. And if in the input-output pair, there is any of them, then we keep the precise, the concrete value. So for example, true, false, there are atoms that appear very often in the code. If there are other atoms that are constructed on the run, for example, during handling of a call that contains specific identifiers that we are not interested in, like they're very specific, then we just treat them as non-deterministic. For integer, only 0 and 1. And for list and tuples, we keep only the first 3 elements. And if there are more elements, we just append a non-deterministic variable at the end. This helped reduce the number of input-output pairs a lot, and allowed also Infer to consider more. Yeah, I have also this slide to show this. Yeah. So the square box represent all the real program behaviors, and the light green circle the behaviors that Infer explores. Since it does under approximation, this is like the way under approximation does. It just considers a subset of all the real program behaviors. So dynamic behaviors provided by dynamic run instead are also a subset of real program behaviors, because by definition they're just concrete data points of input-output pairs. And yeah, this is an over-approximation. But by doing extraction, we mess it a little bit up, right? We provide behaviors that, of course, are a superset of the real behaviors, because we start from them. So we don't exclude any of them. But we can also go and in over-approximation size. So we do this kind of, and we lose soundness. But it's not a problem for us, because we are looking for bugs, and it's okay as long as we don't find too many issues, but this is not happening yet. Yeah, and this is the last slide, is about some experimental results. So I sampled 25 runs that are happening in CI every hour. And for them, I ran specific statistics over like all these specific runs. And like on average, Infer covers around 140,000 functions. So it means that it is capable of provide summaries for this amount of functions. And this is the baseline. This is what is basically 0. And the blue bar is the amount of functions that are provided dynamic summaries. So this input-output pairs. And as a result of providing the blue bars, we get the green bars that are additional functions that can be summarized by Infer only because we provided the blue dynamic models. Right, yeah. And this is the improvement is 2.1 times. So we get 2.1 more times more functions covered. So for which a function can be provided than the dynamic models that we get. So it's quite. This is the interesting result, yeah. So in the end, we get a 3-4% more functions covered, like from the base, from 140,000. But it's surprisingly that giving this dynamic models allowed also Infer to explore 2.1 times the functions, yeah. Yeah, introducing one new summary can potentially result in multiple new summaries. This is what happens, yeah. And we also have an increase in detected bugs on 66% of the runs. Yeah, this is also a positive result. And yeah, this concludes my presentation. Yeah.
Thank you for the talk. I wonder what sources and sinks do you actually use in your taint analysis? Can you tell?
Yes. We use custom sources and sinks, and we track data that we are interested in for privacy purposes. So privacy-sensitive data sources, and sinks are logs in general that log data. And yeah, these are the sources and sinks, but they are manually provided, yes.
Gotcha. And how many of those sources and sinks do you have?
Sources, I think there are not many. There are functions that there are not many. I guess around tens. And for sinks, there are way more, because there can be all the logs places within WhatsApp. Yeah.
Thank you.
I don't know if I missed that. How do you choose the functions that you will pass on to Fausta to get dynamic traces?
Yeah, this is something that I might have forgotten to say. Yeah. So we do an initial Infer run. And from the initial Infer run, we list all the functions that have 0 summaries, so that are not covered. So this is the list of functions that we pass to the tracer for being monitored during the execution. And not all of them end up having traces though. So.
And do you repeat that process?
Every hour, yeah.
I mean, as in with the existing, not with the initial run, but after you provide the first wave, let's say, of dynamically defined summaries,
yes.
Do you then redo this and see which other ones could you, yeah?
We don't do it, but we wrote a paper, it's under review, that provides an algorithm to do it iteratively until a fixed point is reached. And this is, yeah, we didn't test it, but it might be, yes, that providing other dynamic models with this Infer run can help add even more, yeah.
Yeah, and sort of conversely, so you start from the functions with no summaries, but some of them have no summaries because a callee didn't have any summary.
Yeah.
So do you exclude those, or you just take all of them? If you see what I mean.
Yeah, but in the original Infer run, you're talking about the original Infer
Yes,
run.
when you gather the list of functions you want to monitor.
Yeah, we give all of them to the trace, yeah. Yeah, so.
So if I understand well, there is a risk of false positive, and did you any experiment that did you have any experiments that try to understand if there was any in practice an increase of false positive with your approach?
No, because every time we find an issue, especially with tuple, we check in if the prod systems have traces of that particular data being logged for real. So we do like a prod matching of an issue. So this is something that prevents like this unsoundness to reach the developers and to let people waste time on false positives. And it works quite well, and there are no cases where really a false positive reached a developer, bother a developer, and yeah, so especially for this prod matching. But yeah, there can be cases, and but they're under control. This is basically, yeah.
And do you have any plan to complexify a bit the summaries that you generate? So you show us the patterns that you allow in your generated summaries, but you think you generate a real control flow graph with disjuncts. I mean, with branching. Would you be interested in generating more complex summaries at what you currently do? Is there
So it is extensible, like the language for providing input-output pairs is extensible, and for now it only allows to provide this like input-output pairs as concrete values. I guess if we want something more complicated, then we can just have like the some models provided in SEAL. So yeah, so I think it would be better also because it would be compiled, so it would be like an OCaml code, and it would be also faster to evaluate during the analysis, right? Because these also eventually become SEAL models, but they're very simple, right? Just input and output.
Can you share an example of a true positive bug that you found? So something where something leaked from a source to a sink?
Yeah, we don't have it like. No, I don't have anything in the slide, but like in general, so the true positive look exactly the same as an Infer run without the dynamic data. It's just that without it, it wasn't able to produce it. Yeah. So.
Thanks.
Yeah, I think you might have just explained this, but so the dynamic behaviors are input-output pairs. And that gets analyzed by Infer by essentially the equivalent of generating code for that function that says if input equals this, return this, and then Infer analyzes that code, and that's how it introduces its own abstractions to compute its stylus summary. Okay.
Yeah, the code is ignored. The real code of the function is ignored, and instead this input-output pair is used. But the input-output pair is exactly as you said. It's like a function with some inputs and then a lot of conditions. If the input matches this, then this is the output. Yeah.
Okay, I think we will stop here. Thank you very much. And we will start again at 4 p.m.
this works as well now, whatever.
Okay, we will start in a few minutes. I've been asked to remind you that tomorrow there is an event at the City Hall. So you are all welcome at 6 p.m. I think. So our last speaker is Daniel Mercier from Adacor.
Thanks. So I'm Daniel Mercier, working at Adacor, and today I'm going to talk about how we wrote the Ada frontend for Infer. And here's the title, Type-safe nanopasses. You will see that we wrote it by adding many small passes and in a type-safe manner, and I'm going to explain how we implemented that. So first, a bit of context, of course. Infer, we use Infer, well, we developed a front-end for Infer at Adacor that targets SEAL. But first, we needed to go from source to this actual intermediate representation. And for that, we use a tool at Adacor called libLang, which is a tool that we developed at Adacor. And that gives us a parse tree, which is a bit decorated, but it's still very close to the syntax. And you have name resolution that is already done, and you have type for expressions. So that helps quite a lot. But in this talk, I'm going to present the second part, where we went from this parse tree to the SEAL intermediate language. So first of all, let's start by stating how we often compilers front-ends are written. So we want to write many small or smallish passes. And for example, if you want to desugar some nodes, and you're going to iterate that until your language becomes small enough, and you can then simply translate that to your targeted language. So for example, here we're moving a while loop by simply desugaring it into a for loop, sorry, by desugaring it into a while loop with a conditional. But we want to do this in a type-safe manner, in the sense that if you have a later pass that will take as input an intermediate language that has this for loop removed, you don't want to see in the set of constructors that you have to deal with, you don't want to see that there is a for loop there. You want to see only while loops, only the kind of loops that you have to deal with. So that's what the type safety here means. So in this talk, I'm going to present you the NanoPass framework that we actually been very inspired by a framework in Racket called NanoPasses. It's a NanoPass framework, which is mostly used for teaching purposes. But the idea of this framework is that you write very small passes that targets removing one or two nodes or refining nodes, as I will explain. But we are doing that in a type-safe language as OCaml with static typing, which is different than the framework here, which has a dynamic typing system. So to write the front end for Ada, we wanted it to be both maintainable and fully type-safe, which are both very interleaved. And so the outline of this talk, I will start by focusing on small separated passes and why do we want that. Then what do I mean by fully type-safe and why it's important for us to be fully type-safe. And then, as you might have guessed, maybe if you have a lot of intermediate languages, sometimes something that will come is boilerplate because you have to deal with the same nodes in all languages. So we want to avoid that. We want to have as small boilerplate as possible. So let's start by the small passes. So we want small passes, and I'm opposing this to a big monolithic transformation pass. And talking about that because we started by this 4 years ago when we started the Ada frontend. The first thing that we did, and it was a mistake, was to do a big transformation from what libLang gives us, which is, as I said earlier, it's almost a syntax tree, and there's a lot of things in Ada that you need to that are implicit in practice, and that you need to desugar. So this was hard to maintain in the end, And at the end, we needed to add, for example, a feature called control types, which is similar to constructors and destructors in C++. And it was hard to add just because it was targeting from this syntactical tree to seal, and it was hard to implement. So in the end, we went the other way, the other extreme. Why not? So instead of having one big pass, we wanted to implement a compiler front end for seal with a lot of passes, and in particular with passes that target small things, and each pass is doing one particular thing, one single thing, and then the compiler is simply the sequential composition or application of each of the passes that goes from one input language to one output language. So we want the passes to be correct by constructions. And as Julien told us a bit this morning, when in OCaml, when your compiler manages to compile the code, you are already happy because it catches the typing system will catch a lot of kind of bugs. Of course, this is not true in practice. You still have bugs, but it's still an interesting aspect of the language and that you want to take advantage of. And for example, here, one way of making your language more precise only by typing, in this simple example, is in the first case, you have an if statement with an expression as the condition and two branches. The block here, one block is for the else part and the other is for the then part. But a better way to describe that with a better typing would be to have, instead of an expression for the condition, an actual condition, which would be a subset of the expression that are a Boolean type, basically. And as a block, an optional block for the else part, because the else part is not always here. So we want basically each pass to have its own language, because we want to take care of this, we want to have this advantage. And so one pass will take as input an intermediate language, will translate it to an output language, and the next pass will take that as an input, and so on. And each pass will have different language as input and a different language as output. So how are we going to specify all those intermediate languages? So first, how we would do that, naively, let's say, because that's not what we did in the end, you will see. But naively, or often what we are going to do in OCaml is that we are going to use algebraic data types. Each IL fragment will simply be an expression, an inductive expression, or an inductive data type, sorry. And for example, here you have expressions within expression, the subterms are themselves expression, and so on. So you can have mutual types, you could have types that reference others, and so on. What we don't want in this fragment is that we don't want mutable states. So we want pure OCaml fragment, we'll see later why. And often people when writing compiler frontends, they like to have what we call a back reference to the parent. So you're inside an expression and you want to get the expression, the parent expression. That's something that we don't want, because the only way to do that in OCaml would be to add a mutable state. So instead, if you really want to do that, then you could pass the parent down the leaf of the recursive call if you really need the parent. But at least in the typing part, we don't want a mutable state, so we don't want that. So let's go to the second point, type-safe passes. Why? Why is it important? And how are we going to use that? So first, if I ask you what is this pass doing, it's pretty straightforward, only looking at its type. Because you have first a while loop, then you have a while loop and a for loop, and in the second statement you don't have the for loop anymore, so it's pretty straightforward. You are actually desugaring the for loop into a while loop, right? So one of the ways to implement the pass is simply to say that this pass is removing this node from it's removing this statement, so we are desugaring this statement, and you can see it through the type. Another possibility would be to refine the payload. What I call the payload is basically the types of the subterms of the constructor binob, for example, here. And in this pass, we are simply adding the typing information of sub-expression of subterms. So at the start, you had expression without information about their type. And the pass is simply refining that by adding this pair, quote A tip, which is the tip of the expression. So multiple passes also helps type safety, as I hinted a bit earlier. The fact that the language L1 and L2 are different, and when you're removing a node from a language and it doesn't appear in the next language, it's something that we can build on, because when you're writing the ends pass, you know exactly which constructor you have to deal with, and there are constructors that are impossible, and you can see that only looking at the type. It's pretty straightforward, right? So that's also very important. So in this example, the first pass will remove the for loop. The second pass doesn't have to deal with the for loop anymore. So in this example, the second pass is simply removing the condition by adding some if statements within the loop, and maybe using some gotos and label to desugar this while with a condition. And then you go to an infinite loop. But the important information here is that each of the paths knows exactly which kind of loops it has to deal with. So now what are the benefits of this type safety? Why do we care so much about type safety? Type safety helps to catch bugs, of course. In this example, there's a bug here, and since transform is taking an expr1 and returning an expr2, the bug is pretty obvious, and the compiler will tell you that here there is a typing error because E1 is of type expr1 and it is expected to be of type expr2. This is the kind of bugs that we want to find by typing. And the other kind of bugs, and not really a bug, but more a feature of the fact that we remove the node, is that when, after you call transform on E1, you know that you have to deal only with expr2, so you don't have to deal with neg at this point because it has been completely removed. So for the last part, boilerplate free code. That's as I hinted, is very important for us because we don't want to copy paste code all over the place. And the main pitfall of having those multiple intermediate languages is the fact that you will have to rewrite your tree traversal. You will have to rewrite the recursive code and so on. If you have a pretty printer for one language, you will need to rewrite it, maybe copy paste a lot of the code to write a new pretty printer for the other language. But we don't want that. We want either to generate or reuse most of the code. How are we going to do that? So for those three cases here, the tree traversal are actually generating by metaprogramming using simple PPX. I will explain how later. And for which are mechanical, basically the tree traversal, you can look at the structure of the tree and it's pretty straightforward to look at how you are going to do the recursiveness. And we are using what is called in the functional world recursive schemas, if somebody else ever heard about it. And for the pretty printing and the partial evaluation, of course, these are code that is written by hand, and we cannot really generate those. But what we can do for them is that what we want, if you wrote, for example, earlier we saw that there was a binob in L1, and the binob was still there in L2. Then why would you rewrite the pretty printer for this fragment? You don't need to. So that's how we manage to reuse them. If at some laser point you have some language as input, you could reuse most of the pretty printers that you wrote for the nodes that are in the intersection of the two languages, and just write the pretty printer for the new nodes that you added. But since we are focusing on one or two nodes, because we want each pass to remove a node or add a node or refine a node, what should we do with the other? What should we do with other nodes? In this case, that's something that we want to avoid. here, the important piece of code here is the neg, which is being translated, but the second part is simply the recursive traverse of the tree, and that's noise. That could be, that's mechanical, and we don't want to repeat this code all over the place for each pass all going down. So this is the part that we are going to generate, but how are we going to do that? And that's where we are going to introduce a different typing manner to do that, and we introduced heterogeneous trees. Because we want to basically represent partially translated results. The pass will not take into as argument something that is not translated at all, but instead it will take something where the inner nodes have already been translated. And in this example, originally we had two loops, one nested inside the other. And the second loop, when the pass is taking the node into argument, the second loop has already been translated. So you can see in red here that the while loop doesn't have the condition anymore. So the pass that you're writing only takes into as argument something that has partially been translated, where the inner nodes represent already the result of the recursiveness. And for that, we are using recursive traverse, recursive schemas. So maybe you spot something weird with my constructors here. We changed a bit something. We added a backquote at the start, because to do so, we need advanced OCaml typing techniques. And here we use, there are other possibilities, but that's the one we chose. We decided to use polymorphic variants. Polymorphic variants are a bit different than regular algebraic data type, in the sense that if you have a constructor for one, in a normal algebraic data type, you have one constructor that has a name. This constructor is bound to this type. If you have this constructor in another type, they will be different, because they are bound to their own types, which is not true for polymorphic variants. That's a limitation that is removed from polymorphic variants. And those types are actually only the union of their constructors. So in that case, we can use the same constructor for all the languages, and without changing it, and it will be still correct, and it will still type. So then what does the type looks like? So we remove completely so we need the heterogeneous tree again. So we completely removed the recursiveness of the types. We put this out of the type itself and made it parameterized. In that case, you can have a different type for the inner nodes of the expressions and the outer node. And in that case, the two expressions here, what is important is that they are, one is the subset of the other, now that we remove this recursiveness, because if we had expr2 that had expr1, expr2 inside, it wouldn't be compatible. But now it is, because expr2 is strictly a subset of expr1, so both are compatible. And we can now have a type for the inner nodes and a different type for the outer node. So what does a pass look like through its type again? So here is the type of the transform neg pass, which will desugar this neg operator. And the first line is the input parameter, the input type of transform neg. And the second line is the result of the result of the type of the result. So as you can see, the inner node hasn't changed at all. It's still expr2, because as we saw earlier, the inner nodes are already translated, so they are already expr2. And the node that we are taking as argument is a node of type expr1, which has not been translated yet. And that's the only step that we still need to apply when writing the pass. So the pass will look like that, which is kind of cool. You only have the operator that you want to deal with. The E that the neg takes is already of type expr2, so you don't need to do the recursive call. As you can see, the transform neg is not recursive at all. It's a simple function. And since expr2 is a subset of expr1, you can match, that's a syntactical construct. The hashtag expert2 is a syntactical construction in OCaml to match on a type. And here it matches on all constructor of expert2, which is a subset of expert1, and you can return it as it is because it's of the expected type expert2, expert2. So, any questions on this? Yeah? Because I think this is quite important.
Thanks. I wonder, is this some kind of like, you know, in C++ when you do these kind of like nano passes, is using the visitor design pattern? Do you see any parallel between what you're doing in this design pattern?
Yeah, of course. That's something that we actually started with. There is a OCaml library called visitors, which does, it's a PPX that translates, basically it takes intermediate language and generates a visitor. But the issue is that for the constructors that didn't change, you still need to apply the recursive, if you want to change that constructor. If you have a binary binup in the expert1, for example, and you want the same for expert2, it won't work because you need to apply the recursive call and you need to reconstruct the new node with the subterms being recursively translated. So that's why it doesn't really work, but yeah. It's still kind of the recursive scheme that we apply. So what I didn't really say is that this is, of course, you write the pass like that, but then we have a recursive scheme that is applied to this and makes the recursive function at the end. And this is kind of a visitor. Yeah.
I had a hell of a time using NanoPass earlier this year. The whole recursive catamorphism thing really bit me, and I switched to manual recursion. So do you have an example of like the generic recursion thing? Because that's to me seems like the most complicated part. Is
what do you mean by the example?
For the subterms, like you said a generic recursor will handle them. What does that look like?
I don't have it here, but I do have the type. Yeah, I do have its type, which is a bit weird. But basically, it uses what it's using is using a map. So if you take back this slide here, and you use PPX map that would generate a map function for this, it won't generate a recursive map, right? Because it will only generate a map that would apply your function to quote A. Okay, but what you can do is do a recursive function that calls map with itself, and this is what the fold, which is called a fold, it's a generalization of list.fold basically, and this is what the recursive constructor looks like. Actually, we would like to, but we are not. We are generating the map because it already exists. But there are some caveats for generating it for a type, because here is a very simple example with one expression, but we do have mutual expressions. We have L values expressions, so they are both mutually recursive. We have different layers. We have instructions, statements, so you have all of this interleaved, and it's actually 10 lines of code that you need to copy paste each time. So it's boilerplate that is quite fine, but in the end it's still one of our goals is to make this able to generate. So just, yeah. Boris made me remove this. So Boris is the colleague with whom and I had a slide with the typing error that was horrible, and he made me remove it, so I won't talk about this. But yeah, no, to be honest, the types are, so it's actually an issue, because when you're using polymorphic variants in OCaml, the typing error is kind of horrible, because it will tell you that this tag is missing. And when you're using a normal algebraic data type and you're using the wrong type, it will simply say, okay, I'm expecting expert2, you're giving me expert1. But in this case, it will tell you something like, I'm expecting binop or neg or something with things that are and with polymorphic variants in place of quota and so on. So it's kind of hard to understand, but there is something that you can do about it. Is that if you annotate your types for the pass, for transform and neg, if you annotate it correctly, that's not correct typing, by the way, but but if you annotate it correctly, then the typer will tell you you will have a more correct typing error. So yeah, you need to have type annotation, otherwise it's horrible. But yeah, the nano passes is you write the pass, you are getting typing errors, and then you fix them, but at the end you are pretty confident that your pass does what you want. Yeah. Yeah. So, great question. No, not the without. So you could so a polymorphic variant is a union of the constructors, and you can have one type which is a union of a bunch of constructors, another one that is a bunch of other constructors, and you can say that then expert 3 is expert 1 or expert 2. That's possible. But what you cannot say is expert 2 is expert 1 minus neg. And that's the PPX that we wrote. So this is a PPX that we actually wrote, and is a PPX that takes like a record with del add update fields, and you tell him which one of the constructors you want to remove and add, and then it creates the type. So yeah, that's why we had to write. That's the PPX that basically we rewrote. So I have some words for conclusion, and here is a nice graph of our 36 passes, and you can see that many of them don't look too much at the big peak, but most of them are lower than 200 lines of code, which is pretty small in the end, and they are all removing some node, desugaring some nodes, or sometimes the type doesn't really change from the input to the output, but it adds more semantic information. And the only pass that is very big is a pass that basically introduces default values for ADA objects, because in ADA, when you have a variable or an object, there is a lot of default values that you need to initialize for them. For example, pointers needs to be initialized to null. The programmer developer can specify some default values for some of his types, and so we need to include that code. And this is heavily recursive. It looks at all the typing environment, and it does and this is one of the. There's not a lot of passes that does recursive by hand, but this is one of them. And so that also means that if you still want to do recursive by hand, it's not like you cannot do it. So yeah, if there's in some cases there are passes that are harder to write and to make them fit in this framework, but you don't have to be scared and do the manual recursive by hand. Yeah, question.
If I understand correctly, all of these passes are chained.
Yeah.
If you want to make a change after you've written all these passes, if you want to make a change in the middle, how destructive is that? How much? What's the blast radius, right? So if I wanted to change, I guess it would have to be, and I'm not just talking about a code change, actually a type change in, yeah. Can you say a bit more?
Yeah, of course. Yeah. That relates a bit to the question about removing the constructor, because in the end, we also, something that we didn't really present here is that, of course, you not only want to be able to generate your traversal and so on, but you also want to express each of the passes in relation to the precedent. So, and that's what we are doing in practice. In practice, actual union of constructors is only here for the first intermediate language. And then it's just a diff. So you add constructors, you remove constructors, you update them, and you go down the chain. So you can even reverse some of the passes and it will still work. You can add a type at the start and it will still work. So yeah, in the end, it really depends on the things that you are modifying, but you can go a long road by modifying a lot of things and it will still work. But for example, if you add some constructor and you expect it to be removed at some point, you of course need to remove it because it will go down the chain. Something that we also add by the PPX is that the expert2 here, the hashtag expert2, this is pretty easy in this case, but if you remove something and add something else, the diff is not obvious. So the PPX is also adding a type that is called language_common, which are the common patterns between the two. So everything is basically derived with this PPX, and you can add a constructor at the very start of your language and it will be fine. So yeah, to wrap up everything, we think we managed to have a type-safe nanopass in OCaml. We are pretty happy with it. And what we are happy about is also the fact that we have limited magic. We wanted to use most of the features. We wanted them to fit in the language, and we don't wanted our PPX to have too much logic in them. And because you can, if you have a bug in the PPX itself, it's hard to figure out and it's hard to fix. Well, not maybe hard to fix, but at least to figure out that the bug is there. And to give some figures, we implemented this PPX once at the start and we never touched it. So, and it's very easy. I mean, it's just, it looks at the constructors and it adds one, it removes one, and that's it. And then we are relying on the PPX map, which works well. And it's also an easy preprocessor to write. So in the end, we have very little boilerplate. The only boilerplate that we still have is those folds that we still are copy-pasting from passes to passes, but we have plans to make them also part of the PPX. And for us at IDACore, we have this new front-end which doesn't target only SEAL, which is something that we wanted, but it's also interesting for us because we have now a new front-end that could be extended to target maybe other languages. And is of course easy to extend and maintain. And we added at the end, of course it was 1 year of work to re-engineer the front end, and then we managed to implement control types. Maybe we would have managed to write it at first with, with less time than 1 year, but that's it. So yeah, thank you.
So I understand you rewrote your entire front end. So you just ditched the old one and wrote a new one, or were you able to reuse some of your work?
Yeah, for example, the big pass here was actually almost not changed. So, but well, things in this pass had to be changed. But since it's only a pass that goes through the types, and we didn't change the language, the intermediate language for the types, the languages for the type is the same through all the basically the passes. The only thing that is refined is the expression statement and so on. So, but no, we still had to rewrite a lot of code, and we found many bugs in the end, also in the front end. So, yeah, bugs in the first front end that was corrected with the front end, because the really interesting thing here is that when you're desugaring a node into a more basic one, then you can try to express semantically the things in your language with other nodes in your language. For example, in Ada we have something that's called renaming. That so you say X renames Y, and it means that whenever Y, whenever X is seen, you have to basically translate Y, and they are. So it's like X would be a pointer to Y. right? But it's not really that, but it's almost this. And yeah, you can simply write this as a pointer, and it's easier. So you remove the rename, and you have other semantics in the language that can just be leveraged to a renaming. So then you just create this renaming node, and then later passes would just handle this by themselves.
Hello. And how did you flip the switch between the two front ends? Like that seems like a pretty big operation. So you had one front end and now you have another. So were the results very different, or?
No, it was actually fine. Since we are not executing it, thankfully, but we are still using Infer bow. But only in-house, let's say, for testing the front end. So we have a big test suite for the compiler called ACATS, and we run Infer on this test suite with Inferbo, because Inferbo gives more information about values, and it was better for the purpose of testing the front end. So we had not a lot of diffs on this test suite in the end. It was actually okay to. So we relied on on this test suite to find out if the results were good or not.
So taking.
Transforms,
but basically have a way to define it in such a way that it's actually the same result at the end. It feels like based on what those nanopasses are actually doing, it may not be possible. So I'm wondering if you've ever thought about that, or if you have any interest in doing that, or whether that would simplify the implementation even further, possibly.
So is the question about the ordering of the passes?
Right. So it feels like the ordering is fixed in that case, right? Or
not really, because the answer is twofold. So first, not really, because since we are doing diffs between the input language, so we are defining the output language as a diff with the input language. So basically, we're saying the output language is this one plus this node and minus this node, or we refine some nodes. When we refine some nodes, of course, this could go down the line a lot. But if you have, for example, a pass that would desugar for loops and a pass that would desugar an egg, as in this slide, the two can be reversed with no problem. But the other answer to this question is that sometimes the order matter, because in some cases the pass will introduce more nodes, and those nodes will be translated later, and this could cause issues. For example, to give a concrete example, in Ada there's a lot of runtime checks that we want to implement to here. We want to generate code for those runtime checks. One of them being a discriminant check, which will basically check one field of a record against one value. When you access some field, you need this other field to has this value. That's what we call a discriminant check. And there is one pass here that is inserting a lot of record fields, the pass that is basically making default values for the types. But we know that the front end will generate correct field accesses. But if we put the pass that generates the discriminant check after, we are going to generate way too many discriminant checks because of the precedent previous pass. So there are things that we cannot encode really on the typing system that enforces the ordering of the passes. But really, since we are doing those diffs in terms of typing, we could theoretically some of the passes, because of course there are some passes that would expect only this kind of loops to appear, and in that case, of course, you cannot really reverse the passes.
So maybe it's a partial order.
Yeah.
It's a concept. Thank you.
Okay, I think we are done. Thank you very much. So yes, it was the last talk of the day of the workshop. So thanks everyone. Again, thanks all the speakers and all the staff, students, volunteers that help us today. And hope to see you for the next edition of the workshop.